6.1 on the specification, it says explain why some elements can be classed as alkali metals, halogens, or noble gases based on their position in the periodic table. So if it's in group 1, in a really simply put, if it's in group 1, it is an alkali metal. So group 1 are alkali metals. Group 7 are what we call the halogens. And group 8 are the noble gases. And the reason, as you will know from topic 1, if it's in group 1, everything in group 1 has one outer electron in the shell. Because they've only got one electron in the outer shell, they all react in a similar way. Group 7's got 7 electrons in the outer shell, because it's in group 7, so they all react in a similar way. Noble gases, helium has 2 electrons in the outer shell, the rest have got full. The main thing with noble gases is they all have full outer electron shells. If they've got full outer electron shells, then they will be unreactive because they already have full shells. Okay, the rest of this is what I've just explained. So again, this is what I've already covered with you. Right, 6.2. In 6.2, 6.2 on the specification point says recall that alkali metals are soft and have relatively low melting points. Now, the elements in group 1 of the periodic table are known as alkali metals, which we've covered, and have characteristic properties because of the single electron in the outer shell. So they all, from group 1, so they all have one electron in the outer shell. Now, compared to other metals, they're soft. They're very, very reactive. So on the reactivity series is group 1 that comes at the top. They're the most reactive. They have relatively low melting and boiling points. High if you compare it to a glass, but they're low relative to other metals. And they have relatively low density, again, compared to other metals. Now, usually a question that asks you to describe the characteristics or properties, so the properties of group 1 or the characteristic properties of group 1, these are usually foundation questions, but it can come up as a 1 marker in the higher paper too. So we should know the characteristics. Now, 6.3, describe the reaction of lithium, sodium, and potassium with water. So if you look here, and from a foundation perspective, you need to know the word equations. From a higher perspective, you need to know the word equation and the formula equation. So look what happens. Lithium reacts with water, H2O, to make lithium hydroxide plus hydrogen. And you put a 2 here, a 2 here, a 2 here, and it's balanced. That's it. When you react a metal with water, you always make a hydroxide and hydrogen. Now, here it says sodium, and it's got sodium twice, but it's missed potassium. So let's look at potassium. Potassium, in fact, let me ask this as a question to the group. In the chat, can you please tell me the word equation or the formula equation? Pick the one that you can do. If you can do the formula equation, do the formula equation. If you can't, at least tell me the word equation for the reaction between potassium and water. So I'm only going to give you 1 minute. So whoever gives me an answer, well done. Good, but just have to do it as quickly as you can. Excellent. Already got answers through. Fantastic. Okay. So look, all we're doing is, instead of sodium, we're reacting potassium. Instead of sodium, we just put the word potassium. So here, instead of sodium, we're just going to put a K. Instead of sodium, we're just going to put a K. So if the question says, what happens with rubidium and water? Exactly the same. Rubidium plus water makes rubidium hydroxide plus hydrogen. So 2Rb plus 2H2O. In fact, I'll just do it here. Let's get rid of the lithium here. Let's get rid of this lithium here. And all I need to do is swap it with rubidium. And that's it, done. Two rubidiums, two rubidium hydroxide. Yeah, that's all I had to do. What about now if I say cesium reacts with it? So all I'm going to do now is rub out this bit and this bit. And what am I going to write instead? 2 cesium plus 2 cesium hydroxide. So memorize this because it comes up often. Okay, 6.4. On the specification, it says, describe the pattern in reactivity of the alkali metals. Lithium, sodium, and potassium with water, and use this pattern to predict the reactivity of other alkali metals. This is a very common question. Because look at the adjectives that are used. Because all you're doing when you're answering a question on this topic, all you're doing is looking at adjectives to show how reactive something is. So look, lithium, it floats on the water. It fizzes slowly. It gets smaller and then eventually it disappears. When you react sodium with water, it melts to form a ball. So this time it's not just floating on the water, it's actually you can see it visibly melting. Instead of it fizzes slowly, it fizzes quickly. And it gets smaller and disappears. So it quickly gets smaller and disappears. Then potassium, it quickly melts to form a ball. It burns with a lilac flame and it disappears rapidly. So we've gone from slow to quick to rapid. Now, if it says here, so what's going to happen with cesium? We just upgrade the adjectives. We say it melts as soon as it touches the water. It disappears as soon as it touches the water. It sets alight. It explosively burns. But again, when we go through the pre-exam workshop, or even if not the pre-exam workshop, you just go through lots of past papers. When you see questions that are linked to this, it might just say three different metals, A, B, and C, and say put them in order of reactivity. And all you're doing is saying A is the least reactive, then it's B, then it's C. And say give you a reason why, and you just say that it becomes more, the reactions become more vigorous as they move on. But they're the questions I would highly recommend you have a look at so you can see. Okay, let's look at 6.5 now. Now, 6.5, explain this pattern in reactivity in terms of electronic configurations. So it's saying, look at 6.4. Why does it become more reactive as you go down the group? So here is, this is a description of what happens. It becomes more reactive as you go down the group. 6.5 is the explanation why. So first, if we compare lithium to sodium to potassium, what are the different things that are happening here? What's the same is they all have one electron in the outer shell. But as you go from lithium to sodium to potassium, we go from having two shells. So there's in lithium, there's only one shell between the positive nucleus and this outer electron. Sodium's got three shells and potassium's got four. So because the atom's getting bigger and bigger, there's less, the attraction between that positive nucleus and the outer electron becomes less. And because there's less attraction between them, it's easier to remove that electron. So let's see what it says here. This is because the atoms become larger. The outermost electrons are further away from the nucleus. This means the outermost electrons are most easily lost. So memorize this. Try past paper questions on it. Understand the examiner's mindset. If you get the examiner's mindset, this is a nice, simple, straightforward topic. Okay, now what we've got 6.1, that's all of group one done. We've spoke about what the different groups are called, the properties of alkali metals, the fact they're soft, etc. The word equation, the chemical and the formula equations when it reacts with water, the reactivity of alkali metals, a description of how it becomes more reactive as you go down the group, and finally, the last part of this part of set of topic 6 is just explaining why they become more reactive as you go down the group, which means we can now move on to 6.6. So 6.6 all the way up to 6.13 is now group 7. Okay, so 6.6, the appearance of halogens. So in the specification, it says recall the colors and physical states of chlorine, bromine, and iodine at room temperature. So we need the colors, which are here, and the physical appearance. So just before we get to that point, fluorine, chlorine, bromine, iodine, all of group 7 are always they're non-metals and consider molecules made of pairs of atoms. So it will always be F2, Cl2, Br2, and I2, meaning one fluorine is attached to another fluorine. Or if, just in case it comes up as a covalent bond because it's linked to topic 1, it means it will look like this. Both fluorines share one electron each, with 6 remaining. Let me just get rid of that. And this fluorine here, from its 7 electrons in the outer shell, it shares 1 and it has 6 on the outer layer. So it's a covalent bond. That's what that line is representing, a shared pair of electrons. Okay, now appearance. The appearance, and this is what you've got to remember, the appearance becomes darker as you go down the group. So it starts a pale yellow, green, orange. Iodine is a grey solid, which forms a purple vapor. So fluorine's a pale yellow gas, chlorine's a green gas, bromine is an orange liquid, and iodine is a grey solid, which forms a purple vapor. Now, after this, if I said to you, astatine, what does astatine look like? Then it would be a color that's darker than a grey solid. So you say astatine is a dark grey or a black color. Okay, now the next thing you need to know alongside that is that fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. So what does that make astatine? Solid. And tennessine is also a solid. So the pattern here is it goes from gas to gas to liquid to solid. So gas to liquid to solid as you're going down the group. So from a color perspective, it becomes darker. From a gas liquid solid perspective, it goes from being a gas to a liquid to a solid. Okay, so what happens to the properties of the elements in group 7 as you go down? You go down the group. So group 7. So 6.7 on the specification point says describe the pattern in the physical properties of the halogens chlorine, bromine, and iodine, and use this pattern to predict the physical properties of other halogens. So we know that melting and boiling points go up as you move down the group. So as you go down the group, the melting point and boiling points increase. So fluorine is the lowest, chlorine is going to be higher. The halogens get darker as you go down the group. We've already kind of covered this in the previous topic, in the previous slide. And the halogens react in a similar way because they all have 7 electrons in the outer shell. The whole point of 6.7 and what they want from 6.7 is that as you go from fluorine, chlorine, bromine, iodine, now it says astatine and it says what state is it going to be? Predict its state. We're going to say, yeah, solid. We know that one. If we say what its color is going to be, we know that it's going to be a black or a dark brown, a dark gray color. Melting points and boiling points go up as you move down the group. Astatine is much, much lower, so it's going to have a bigger melting and boiling point than iodine, for example. Okay, test for chlorine. Now, when you test for chlorine, chlorine is a gas. So you dip damp litmus paper. The reason why the litmus paper is damp is because that way the chlorine can dissolve into the water. Because chlorine is a gas. And that gas is not going to attach itself to a solid piece of paper, but it will dissolve into water. Now, when you add it to the chlorine gas, the litmus initially it bleaches. Well, initially it turns red, then it bleaches and turns white if chlorine is present. So you dip damp litmus paper into the gas. If it goes red and then turns white, that shows that chlorine is present. So this is one of those topics that come in both paper 1 and paper 2, the test for chlorine. Okay, reactions of halogens. How do halogens react with hydrogen and metals? Now, halogens can react with hydrogen. For example, chlorine reacts with hydrogen to form hydrogen chloride. So Cl2 plus H2 becomes HCl. Now, hydrogen chloride. So now if we, instead of chlorine, we said fluorine, then it's going to make hydrogen fluoride. Instead of fluorine, so we got fluorine, chlorine, bromine, iodine. Instead of chlorine, we react bromine. It's going to make hydrogen bromide. Instead of that, we use fluorine. Fluorine reacts with hydrogen to make hydrogen fluoride. Instead of chlorine, we use iodine. So iodine reacts with hydrogen to form hydrogen iodide. And look, Cl2 plus hydrogen makes HCl. So that means F2 plus H2O makes HF. There should be a 2 here. Now let's do it with bromine. You see, all I'm doing is swapping the chlorine out with the new thing. Bromine plus H2O. So just hate the hydrogen, not H2O. Makes 2HBr. Now let's do it with iodine. I2 plus H2 becomes 2Hi. So once you remember the formula once, you've got it forever, as in for whatever you add to it. Now, halogens also react with metals. For example, chlorine reacts with lithium to make lithium chloride. Cl2 plus 2 lithium makes 2 LiCl. So what about if we did the same thing with fluorine? Then same thing, F2 plus 2Li becomes 2LiF. In this case, you can change the metal as well. If I did bromine instead, it would be Br2 plus 2 lithium becomes 2LiF. So again, please memorize this. Important. Okay, 6.10, reaction of halogens. Halogens react with hydrogen to make hydrogen halides. So that's what we've just covered. Hydrogen reacts with halogens to make, this is a hydrogen halide. Now, if we add this hydrogen halide into water, let's use HCl as an example. We add it to water, what's going to happen to it? It's a strong acid. It's going to dissociate completely into H plus and Cl minus. So chlorine reacts with hydrogen to make hydrogen chloride. Hydrogen chloride dissolves in water to form hydrochloric acid. And that's because when it enters water, it dissociates. So it becomes H plus, which is the acid part, and Cl minus, the part that can bleach skin, bleach other things, kill off bacteria, etc. So how does a more reactive halogen displace a less reactive one? So a more reactive halogen can replace a less reactive halogen in its salt solution. For example, chlorine reacts with potassium bromide to make potassium chloride and bromine. So what we're doing here is we have chlorine and we have bromine. Now, which one is more reactive, chlorine or bromine? So F is the most reactive, fluorine, then chlorine, then bromine. As you go down the group, they become less reactive. Then iodine, then astatine, which we don't need to know too much about in year 11. So chlorine is above bromine, so it's more reactive. So it swaps places with it. It pushes it away. So an example I've given in the past is I've got a pen. One of yourselves, you're young and strong, and you think, oh, I want Mr. Tanvir's pen. So you come along, you grab my pen, and because you're stronger, you're able to take my pen from me. That's what's happening here. Bromide has got one of potassium's electrons. When chlorine comes along, chlorine's a lot stronger than bromine, so it takes that electron for itself. So now it's become chlorine minus, and it attaches itself to the potassium to become potassium chloride. The bromine goes back into the solution. The bromide part goes back in solution and becomes bromine, which is Br2. So you can see the equation there. What's happening? Chlorine is more reactive than bromine, so chlorine has replaced bromine in this reaction. Now, bromine is a reddish color. So because bromine is a red-brown color, so when it's displaced, you'll see a red-brown color change. Because it's a brownish color, this is what's entered the water, entered the solution. So as it enters the solution, it's going to turn it into a reddish-brown color. Okay, now when displacement reactions happen, now this part of the lesson is specifically triple, not triple, sorry, higher. Not triple, is higher. None of topic 6 is triple, um, as is none of topic 7 or topic 8. There's a separate topic, which is topic 9, which we'll be doing at the end of the week, that is specific to triple. So this is higher. So what we're saying here is when a displacement reaction occurs, oxidation occurs, reduction occurs. So oxidation is when oxygen is gained or there's a loss of electrons. And reduction is when oxygen is lost or it is a gain of electrons. So oil rig. So let's have a look at this. Why is this a displacement reaction? So what's happened is chlorine is reacting with potassium bromide to make potassium chloride plus bromine. So chlorine is Cl2. It's just, we write it as Cl2 and no charge because it's an element. Elements don't have charges. Because the elements don't have charges, I'm going to redo this at the bottom here. We just write as Cl2, no charge. Now potassium bromide. Potassium had 1 electron in the outer shell. Bromine had 7 electrons in the outer shell. So potassium has given its electron away. So potassium has become K plus. Bromine has become Br minus. So that's potassium bromide. K plus, Br minus. Now with potassium chloride, it's the same reaction as this, except with chlorine. So we've got K plus and Cl minus plus bromine. Now bromine is Br2. Now the next thing we've got to do is we've got to delete. It says potassium ions appear on each side, so we can rewrite this as that. So we're going to get rid of K plus because it doesn't change. Look at Cl2, it goes from having 0 charge to being -1. The K plus is K plus there and it's K plus there, so we delete the spectator ion. And Br minus has gone from minus to Br2. Now what I'm going to do is I'm going to delete this because did you see this formula here? That's exactly the same as what I've just drawn. So let's use what's already drawn. So what's happening here is, let's look at each element one at a time. We've got Cl2, and Cl2 has become 2Cl minus. Now, what has to happen to chlorine for it to become negative? In anything, when we're talking chemistry, we're talking from a chemistry perspective, what does an atom have to do to become negative? It has to gain an electron, and then it becomes a negative ion. So here, it gains an electron, or in this case 2, because we've got 2 chlorines, to become 2Cl minus. Now let's look at bromine. We have got 2Br minus, and it becomes Br2. Now, if something's negative, how does it go back to being neutral? So in this case, it's negative at the moment, 2Br minus. It needs to get rid of something. It needs to get rid of its negativity. In other words, it has to lose its electrons, which you show on this side. Because there's 2 bromines, 2Br minuses. That's what 2Br minus means. It means one of them, 2 of them. So it has to lose 2 electrons, one from each. 2 electrons. Now that means chlorine, Cl2, has gained electrons. So that is reduction. The 2Br minus, the bromine ion, has lost electrons. So that is oxidation. And that's what this slide's showing. That chlorine gains electrons to become 2Cl minus, and bromine loses its 2 electrons to be to become oxidized. Okay, 6.13. Like we are now out of the higher topic. And we're back into combined. So 6.13, 14, 15, and 16, the rest of this session will all be for combined and triple. So 6.13 says explain the relative reactivity of halogens in terms of electronic configurations. So this is similar to what we covered in 6.5 for group 1, where we explained why the reactivity increases as you go down the group. Now with 6.13, it's the other way around. So if this is what it shows on your paper, on your document, please change this. It's the other way around. It's more reactive as you go up the group. Actually, no. What the way they've shown it is fine. Sorry, that's my bad. So the way it's been shown here is absolutely fine. It becomes less reactive as it goes down the group. And why does it become less reactive? Because as you go down the group, the halogens become less reactive. Why? The atoms get bigger. Because you're adding one extra shell each time. That means the outermost electrons are further away or farther away from the nucleus. So there's your positive charge, there's your outer electron. So the outermost electrons are further away from the nucleus. The result, it becomes hard to gain electrons in the outermost shell. So if this electron comes along from sodium, sodium has just lost its electron. That electron is more likely to go to the fluorine, because the fluorine is a smaller atom, so there's more attraction between the positive nucleus and the outer electron. Okay, we're on to noble gases. So 6.14, noble gases. Why are noble gases unreactive? So helium is the exception as it only has 2 electrons, but that's still a full outer electron shell. So noble gases are very unreactive. This is a question that comes more in foundation, but I've seen it in higher paper too. But it's just worded a lot more difficultly, in a difficult manner in the higher paper. But it's something that comes towards the end of the paper in foundation and beginning of the paper in higher. So noble gases are very unreactive and rarely form molecules because the atoms have stable electron configuration, meaning they've already got 1, 2, 3, 4, 5, 6, 7, 8. So we're talking about a noble gas here that's got 8 electrons in the outer shell. Let's do neon. So neon's got 8 electrons in the outer shell. That means it doesn't need any extra electrons. So no, the electrons are going to get there. So if any electron does come close by, it doesn't make a difference. So here's the electron. The neon is not bothered about that electron because it already has a full outer electron shell. So they're relatively unreactive and they rarely form molecules. So it's unlikely you're going to see something like this. Helium 2, neon 2. Because these are they're not very likely that they'll be made. Now, all of the noble gases, other than helium, have 8 electrons in the outer shell. Again, giving them stability. They don't need the extra electrons. So, helium. Now, this is sometimes where the higher stuff kicks in, so it's important to know this. You should know the use of each noble gas and also the explanation. So, helium is a lifting gas in party balloons and airships. How does it actually do that? It's less dense than the air. So, that means helium floats away. Argon. It's a shield gas when welding. So when you're burning something with flame, um, I'm just trying to think what an example. So you can use like a flame torch when you're cooking, for example. So you've got a flame torch and it's got flame coming out of it. The flame so that's more like a bird. The flame that comes out of when you're doing wielding, sorry, you're doing welding, so as in you're melting some metals and joining them together, you use argon gas to stop it reacting with the oxygen in the air. It's denser than air, so it stops air getting to the metal. So it's inert, so can't oxidize the metal. Krypton and xenon, it's a gas with filament bulbs. What krypton and xenon actually does, it stops the light from overheating. Now, explanation is inert and so won't react with the hot filament in the bulb. So it stops chemical reaction, it stops the metal reacting with oxygen. Okay, this is the last part of the chemistry section for today. Properties of noble gases. What are the elements in groups and what are their properties? So we've got helium, neon, argon, krypton, xenon, radon, and whatever the last one is. Or organeson. So the elements in group 0 of the periodic table is known as noble gases. As you move down the group, the boiling point of these gases get higher. So, for example, xenon will have a much higher boiling point than helium. So the lower you go down, as you go down the group, the boiling point increases. This is because the molecules are getting larger, and as they get larger, the intermolecular bonds that form between them, because they can't form anything other than intermolecular bonds. So that's because the intermolecular bonds become larger, which makes them forces the intermolecular bonds stronger between them. So as you get a larger and larger atom, the intermolecular bonds in between the two become larger as well. I mean, it's still not a high temperature, but the temperature still increases as you go down the group. As a result, so the stronger the intermolecular bond, let me get rid of this and read that out again. So this is because the molecules become larger, which makes the forces between them stronger. As a result, more energy is needed to break these bonds. So again, important bit to memorize. So 7.1 and 2 are linked to the core practical and all the different practicals that we can do and how we can use different types of equipment to investigate the effect different factors have on the rate of reaction. So as you can see in this diagram, the one that's in front of you, if you get some metal and, for example, add it to an acid, it will release hydrogen gas. The hydrogen gas will diffuse away, and that can then be collected in this syringe. And you can measure what the volume of gas is at fixed time intervals. So you get a change in time. So I do it 30 seconds, 60, 90, 120. But it has to be one of your control variables here would be then the amount of time you measure it for. And then your volume would go in the next column. Now, if you've got volume and you've got time, you can work out the rate of reaction. So you draw your graph and then at a certain point you draw a tangent and work out the rate of reaction. That's going to come in a few more slides. interpreting graphs linked to rates of reaction. Now, whenever you answer any question linked to this, particularly if you're writing a 6-mark question and you've been told to talk about the method on how to investigate or anything like that, you always start by You need to make sure you mention within the method, you need to mention the independent variable. That's the one that you change. The dependent variable, what you're measuring, and then your control variables, whatever you're keeping the same. And if you're talking about your independent variable, talk about what you're going to change, how you're going to change it. Dependent variable would be what you're measuring and how you're going to measure it. Control variables again, how you're going to control it. Or for example, if you're using 50 centimeter cubed of acid, what would you do? Or you would use a measuring cylinder to ensure it's 50 each time, that kind of thing. Now, when you're investigating different factors, one of the things you can do in this experiment is you could change the surface area of the reactant. So with control variables, some of the time they can be easily changed into independent variables. So you could make surface area of the reactant your independent variable. You could do the experiment where you've got the metal as a large piece. Then you could do it when it's been broken down to small pieces, and you could do it finally as a powder and see what happens to the rate of reaction across, for example, 5 minutes or 10 minutes. Because that would be one of your control variables, keeping the time the same. The concentration of the acid, you could repeat the experiment using different concentrations, or you could do it at different temperatures. Okay, so this is another way of doing it. You get this white slate or piece of card, you put a cross on it, you add your chemical, your solid and your liquid, you add your chemicals, and when they react, no, sorry, you add two different liquids into this, and they form a precipitate, which is a solid. And as the precipitate starts to form, the X that's on the piece of paper underneath disappears. So you measure the time taken for that X to disappear. So the method is you put 50 centimeters cubed of sodium thiosulfate solution into a conical flask, put the container on a cross drawn on a piece of paper, put the conical flask over the top, add your two liquids, add 5 centimeters cubed of dilute hydrochloric acid and start timing, and time how long it takes for the cross to disappear. Now, what you can do the next time round is use a stronger concentration of the sodium thiosulfate or a stronger concentration of the hydrochloric acid. You could do the experiment again at different temperatures. The key point here is then to do it 3 times, remove any outliers, and then take an average. So outliers, anomalous results, same thing. So how can you determine the most appropriate practical method for finding a rate of reaction? So you use the apparatus above when a gas is made. So if you know a gas is being made, you would use this. If a solid is being produced when you react to different chemicals, you would use this one. So if it's a gas that's being produced, use this one. If it's a precipitate, in other words, a solid, then use the X marks the spot one. Okay, collision theory. When a reaction occurs, two things have to happen. So collision theory states two things have to happen. Number one, a collision has to occur. And number two, not only does a collision have to occur, they have to have activation energy, meaning the minimum amount of energy needed for a reaction to occur. So if you think about a piece of paper, if I was to, a piece of paper will burn in oxygen. But right now, I have a piece of paper right next to me. There's oxygen in the air. Why is it not burning? And the reason it's not burning is because although the oxygen in the air is colliding with the paper, they don't have activation energy, so they do not have enough energy to make the reaction happen. So whenever we answer any question linked to rate of reaction, we always have to link it to collision theory. Always, always, always link it to collision theory. As in, is there enough collisions happening? And when the collisions are happening, do they have enough energy to make the reaction happen? So collision theory, based on this, there's different factors that increase the rate of reaction or slow down the rate of reaction. So if you increase the temperature, that will increase the rate of reaction. If you increase the surface area, that will increase the rate of reaction. Now, when we say increasing surface area, we mean if you've got a block of something, then only the outer surface can react. The inner surface can't react. Increasing surface area means breaking it into smaller pieces. So now I've broken this big cube into 4 smaller pieces, or there's so much additional surface that's available to react. If I take those and I turn it to powder, now there's lots more surface available to react. Then we've got catalysts, which speed up the reaction and provide an alternate pathway. And the alternate pathway means less activation energy is required. But the catalyst itself does not become part of the reaction. The next one is concentration of reactants. If we increase the concentration of reactants, we've got more particles and increasing the pressure. That means there's less space for the particles. So let's go through each one at a time. So what happens if we've got now these questions, past paper practice and memorization, very important here. So if you increase the concentration, why is that significant? Well, increasing the concentration of the reactants means you've got more particles. If you have more particles, it's more likely it's more likely there will be successful collisions. It's more likely there'll be more particles with activation energy, so there will be more collisions and more successful collisions, which means the rate of reaction increases. But you see how we linked it back to collision theory? More particles means more collisions. Now pressure. If you've got all your particles in this much space, if you decrease the space, in other words, increase the pressure, the particles are now closer to each other. So that means there's going to be more frequent collisions and the rate of reaction increases. If you increase the surface area, it's what I showed before, only that surface there can react. So if I break it up, all this extra surface is reacting. So that increases the rate of reaction. If you turn to a powder, then you've got lots of surface reacting now. So increasing the surface area means making it in smaller so that there's more frequent collisions. There's more particles available to collide. And what does that do? That increases the rate of reaction. If we increase the temperature, what effect will that have? That means two things. If you increase the temperature, particles have got more kinetic energy, which means they're moving faster and they have more activation energy. So when you increase temperature, you've got to look at this from two perspectives this time. You've got particles moving faster, and you've also got particles uh, that have got more activation energy. So this way, because you've got more because particles are moving faster, you'll have more collisions. Because you've got particles with more activation energy, more energy, it means more of the collisions will be successful. So overall, the rate of reaction increases. Okay, now interpreting graphs. So it's what I said to you before. When you're working out the rate of something, what does rate of reaction mean? rate of anything means grams divided by time or volume divided by time. So rate of reaction is measured in grams per second or centimeters cubed per second. So when you're working out a rate of reaction of something, it's going to be the mass divided by the time, or it'll be the volume of something divided by time. And don't forget, what do we measure time in? We're measuring time in seconds. That's why that's seconds, and that's why that's seconds. So let's have a quick look at this question. We've got rate equals the quantity formed divided by time. Now, time should be in seconds, so we need to convert that. 2 minutes equals 120 seconds. Calculate the rate of reaction when 234 centimeters cubed of gas is produced in 2 minutes. What's the rate of reaction? So we know quantity formed is 234. We're going to divide that by the time, which is 120. So the answer is 1.95 centimeters cubed per second. So here's some practice questions for you to try in your own time. But one thing to keep in mind is we have to convert the 1 minute into 60 seconds. Here we've got 2 minutes, so we're going to convert it into 120 seconds. Here's 1 minute again, so we're going to convert it into 60 seconds. But otherwise, this is just a matter of substitute the numbers in and answering the questions. Okay, how can we use graphs to determine the rate of reaction? So we can use see if there's another example. Let's use this example. Now, this is a plotting graph example, but I'm just going to use this example to find out what the rate of reaction is. So if I said, what is the rate of reaction at 25 seconds? What you need to do is go to 25 seconds. Now, this is already a straight line, so let's draw the straight line down. Now, if you can work out the gradient, automatically you've also worked out the rate of reaction. So gradient equals, so m is the gradient. In fact, we'll just write rate of reaction equals change in the y divided by change in x. So what's our change in y? 0.3. It's from here to here. And divide that by the time, well, the change in x, so 0 to 25. So it's going to be 25. And it's just a matter of using your calculator and working out whatever that is. So that way you know that 0.1 something, 0.12 is, yeah, 0. Yeah, 0. Roughly 0.12 grams are being used up every second. So another one. This question is a little bit different. It says, if you were asked what the rate of reaction was between 0 and 60 seconds, you could use the graph to find the quantity of gas made. So let's have a look at this. Because this time you're looking at from 0 to 60 seconds. So again, you're doing y, change in y divided by change in x. But you're not looking at a specific point, you're looking at between 0 and 60. If I said, what's the rate of reaction at 40 seconds? That would be it. Then you'd have to draw a tangent and work out a gradient of that line. But we're looking from 0 to 60. So from 0 to 60, what's the change in y? The volume of gas produced goes from 0 all the way up to, that's about 48. So it's 48. And what's the change in time? 60. So it's 48 divided by 60. So the answer, the rate of reaction is 0.8 centimeters cubed per second. There you go. Now, this particular question is a little bit different. So look, in this question, it said rate of reaction was between 0 and 60. What was the rate of reaction between those two times? This time, they're saying, if you are asked to estimate the rate of reaction at 40 seconds, saying, what's the rate of reaction at 40 seconds specifically? So let's have a look at the rate of reaction at 40 seconds. They've drawn a tangent. There's 40 seconds just there. There's the tangent. Now you're looking at the change in y and the change in x. So what's the change in y? It starts from 31 and goes up to 50, so that's 19. Divided by, that's 20. 10, 20, 30, 40, 50. And that's going up in twos, 52, 54, 58. So 58 take away 20 is 38. So we do 19 divided by 38. So the rate of reaction is 0.5. And now this is in centimeters cubed. So the units will be centimeters cubed per second. Now this thing's in my way, so I can't show it. Whoops. So it'll be centimeters cubed per second. Okay, so what is a catalyst? It's a different reactions need different catalysts. Usually catalysts come from the transition metals in the ones in the middle of the table. Enzymes act as catalysts in biological systems. So when we talk about protease in biology, protease, carbohydrates, lipase, they were biological catalysts. Because they were substances that sped up the reaction without become part of the reaction. Now, from a chemistry perspective, a catalyst is a substance that lowers the activation energy of a chemical reaction but are not used up themselves. And the reason they do that is because they provide an alternate pathway. By providing an alternate pathway, they lower the activation energy, so they speed it up without becoming part of it themselves. So it's a little bit like this. A person needs to drive over a really big hill. They've got either that trip or they can drive over two mini hills. They know their car's going to struggle going up this really big hill. So what's easier? It's easier to just go over these two small hills. Now, if you add up the height of those two small hills, it's the same as that large hill, but it's just easier. Less energy is needed to go over these two. So, catalysts. What happens to particles and the required activation energy for reactant particles is reduced. So, the main thing is the activation energy needed to make the reaction actually happen. With the catalyst, it's less. So, the frequency of successful collisions with enough activation energy increases. So what happens to collisions? The number of successful collisions increases because now more particles have got activation energy. What happens to the rate of reaction? It increases, and this is your measurement, grams per second or centimeters cubed per second. Okay, now cover this in topic 4, sorry, when you did paper 1, and it was covered in the last AMALathon as well. By that I mean these reaction pathways. So a substance that lowers the activation energy of a chemical reaction. So a catalyst is a substance that lowers the activation energy of chemical reaction but are not used up themselves. So different reactions need different catalysts. Enzymes act as catalysts in biological systems. Catalysts increase the rate of reaction by providing a different pathway for the reaction that has a lower activation. So this is what we can see here. A lower activation energy has been provided One second. So in this reactivity profile, you can see this was an endothermic reaction. And we know that because the reactants have taken energy in, which is why the products have got a higher level of energy. Now, the difference made by the catalyst is this was the amount of energy needed for the reaction to start. Now only this much energy is needed. Hence, because it has a low activation energy. So make sure you know how to draw this. Okay, enzymes. Enzymes are biological catalysts. Enzymes can be used in the production of alcoholic drinks and many other things. Okay, what happens in chemical reactions in terms of energy? But the rest of the biological catalyst stuff is stuff that we covered in topic 1, in B1, linked to enzymes, knowing a little bit about the digestive enzymes and so on. The fact that enzymes have specificity, that they become denatured at a certain temperature, all these things could link to this part of the topic. So it's important to know those connections. So what happens in a chemical reaction in terms of energy? So energy is conserved in chemical reactions. This means that the energy that goes into a reaction comes out of the reaction. That's conservation of energy. So conservation of energy is a law that states the amount of energy in the universe at the end of a chemical reaction is the same as before the reaction takes place. In other words, energy cannot be created or destroyed. It just transfers from one place to another. So even if we have whatever we're doing, even if you have a chemical reaction, the amount of energy that goes into the reaction is the amount of energy that's released from the reaction. Now, when we have reactions, some reactions take energy in, some reactions release energy. So endothermic and exothermic, which we are aware of. So what are examples of reactions that release heat? So if something releases heat, what do we call it? Exothermic. If something takes in heat, then we call it endothermic. So these are examples of reactions that release heat. Reacting something with oxygen, so combustion, neutralization. Well, this is similar, but reacting oxidation reactions are reacting things with oxygen. Displacement reactions. All these reactions release heat energy. So what are examples of reactions that take in heat? So salts dissolving in water, citric acid and sodium hydrogen carbonate. Um, this is thermal decomposition. So that potassium permanganate is being heated up, and because of the heat, it'll break apart into different, well, in this case, mainly oxygen gas, and then a solid will be left behind. So how can we tell if a reaction is endothermic or exothermic? Now, if a reaction is happening, if you add a thermometer to the reaction, if the temperature increases, that means energy has been released. That is exothermic. If you add a thermometer and the temperature goes down, that means heat energy is being taken in. And that means it's an endothermic reaction. So if we look at these reactions, although the answers are here, you can cover them up afterwards and have a go. So in the first reaction, our start temperature is 21, end temperature is 14, which means our change in temperature is -7. So that's endothermic because energy has gone in. In the second one, hydrochloric acid, sodium hydroxide, so the neutralization reaction, it starts at 25, it goes up to 45, so plus 24 degrees. And that means energy has been released, so that's exothermic. And carbon and oxygen releases Increase the temperature by 1079 degrees, which means a lot of energy is released, so it's exothermic. So an exothermic reaction is a reaction that transfers energy into the surroundings. So knowing examples of it is it can come up as a 1 mark question. So it's important to know combustion, oxidation reactions, displacement, neutralization. So what can we use? What uses do we have for exothermic um, reactions? We can have self-heating cans, which works in a similar way to hot heat packs. Some sports injury warm packs use exothermic reactions. So again, hand warmers, heat packs, that kind of stuff where you click a little button or you break something inside a packet and the reaction releases lots of heat energy. Okay, now what are endothermic reactions? So this is a reaction that takes in energy from the surroundings. So for example, thermal decomposition and salts dissolving in water. And what uses do we have for endothermic reactions? So this is taking heat energy out of the surroundings, meaning everything around it becomes cold. So it can be used. So some sports injury cold packs use endothermic reactions. So this is something we've probably seen in school where someone's got injured and they've been given a cold pack. Some schools just use like a thing that goes into the freezer. I know one of my old schools did that, and I've also seen schools where it's an actual cold pack. So you press the little thing inside, it releases the chemical, the chemicals react, and they react in such a way that it cools the whole of the surrounding, so it freezes up really fast. Okay, making and breaking bonds. So what happens to bonds in chemical reactions? So hydrogen and oxygen break apart to make water. So what actually happens is the bond here is broken, this bond is broken, these bonds are broken, and then they reformed, joined together as water. Now, what you need to remember here is bendomex. When bonds are broken, that's endothermic. When bonds are made, that's exothermic. That means in every single chemical reaction, you get bendo. Now I've written bendomexo for some reason, but it's bendomex. You can remember it as bendomex or whatever you want to remember it as. So because every single chemical reaction, the bonds have to break first, which is endothermic, and new bonds have to be made, which is exothermic. Now, we know a reaction is, now we've just been saying that this reaction is endothermic. And now I'm telling you that what happens in thermal decomposition is endothermic and exothermic. But then why do we call it endothermic? We call it endothermic because the endothermic part of it uses up more energy. So more energy is taken in because it's endothermic than released. So it does have an exothermic element to it. Energy is released when the new bonds are made, but it's not as much as the amount of energy that was taken in when the bonds were being broken. So in every single reaction, you have the breaking of bonds and the making of bonds. Whichever one releases or takes in more energy is what that reaction is overall. So energy must be supplied to break bonds in the reactants. The energy supplied is the activation energy. This process is endothermic. So what we just said, bendomex. Bendo breaking is endothermic and making is exothermic. So that's what they're saying here. When you break bonds, it's endothermic. And that's what it's saying here. When bonds are made, energy is released, so that is exothermic. So in an endothermic reaction, the energy taken in to break existing bonds is greater than the energy released from forming new ones. So Here's the reactants. It takes in lots and lots of energy. So all the way from here to here. That represents endothermic. Because at that point, the reactants, the bonds are being broken. Once the bonds are being remade, this much energy has been released from here to here. That's the exothermic part of this reaction. So which one is it? What do we call this reaction? We will say it's an endothermic reaction because there's more energy that was taken in and given out. So energy in is greater than energy out, so hence we call it endothermic. And if you look at this energy profile, in an endothermic reaction, the reactants always have less energy than the products. Why do the products always have more energy? Because in an endothermic reaction, the energy is being taken in. So the internal energy is always going to be higher. In exothermic, the energy is being given out. Because it's giving the energy out, the final energy will be lower. So we need to be able to calculate energy changes. So this is this part here that I'm going to show you an example. And then when we do the pre-exam workshop for chemistry paper 2, there's going to be a lot of question on this topic. 7.14, the calculating energy changes comes up at least once every 2 years. And if you know how to do it, it's an easy 4 or 5 mark question. So it is important that we can do this. Now, the energy needed to break bonds and the energy released when bonds are formed can be calculated from bond energies. So the overall energy change, so if I just go back to this 1 second, the overall energy change is going to be whatever this is, take away whatever this is. In other words, that gap there. But we can work that out mathematically. So it's the sum of the energy needed to break the bonds, so the endo. So we're looking at the reactants minus, take away the sum of energy released when bonds are made. So sum of energy released when bonds are made. So that is Excel. So let's see how the question works. So here's our reactants here, and here's our product. Now, in this question it says, the equation for the reaction can be represented as, so we've got C2H4 plus Br2 becomes C2H4Br2. Now it says use the bond dissociation energies. That's the energy here. That's the energy that's released when a bond is broken or made. The averages. And it says use this information in the table to calculate the enthalpy change for this reaction. So this is what you do. Let's work out this side first. So we've got one carbon-carbon double bond. That's 614. So if you break a double bond, how much energy is released? Or how much energy would it take? 614. So we're going to write 1 times 614 plus how many CH bonds do we have? 1, 2, 3, 4 plus 4 times this one. And we've got a BR bond. So we're going to add to that 193. All in all, that equals 2,459. So we've got this number now. Now let's look at the other side. So this time we're breaking one carbon-carbon bond. That's here. So that's 348 plus 1, 2, 3, 4 CH bonds. So that's 4 times 413 plus 2 CBr bonds. So that's this one at the bottom. 2 times 276. Now altogether that equals 2,552. Now you take away those numbers, you get minus 93. Now, because energy has been released, as in this is this side here, this is the exothermic side. Because we have a negative number, which means the reaction was exothermic. We know it's exothermic because energy has been released and lost to the surroundings. That's why we have a negative number. It's been released. If you have a positive number, that's energy that's been taken in. Right now, I would advise after our session today, have a go at these type of questions in your past papers. Try and have a go before we do our pre-exam workshop. I'm saying try and have a go, but we've got not this weekend, but the weekend after, so you've got plenty of time to be getting through lots and lots of past papers. Okay, now we spoke about activation energy already. It's the minimum amount of energy that particles must have to react. So chemical reactions can occur only when the particles collide with sufficient energy, and that minimum amount of energy is known as activation energy. Okay, reaction profiles. You need to memorize these. You need to know which one is which. So look, here, the reactants have got less energy, the product's got a greater amount of energy. So that's going to be endo. Because it's taken energy in, it's released a small amount of energy, the products have more energy. The product has more overall energy, that means energy has been taken in. Now here, and sorry, so you know this initial bump from the way it says reactant all the way to its peak, that is your activation energy. That's the energy needed to make the reaction occur. Now here, the initial reactants have got more energy. So this initial energy here is the activation energy. So make sure you know how to label activation energy. And once the reaction has occurred, for example, a piece of wood reacting with oxygen, carbon reacting with oxygen, it releases lots and lots of energy. That's why the products at the end have got less energy. So these are reaction profiles. Learn them for endo and learn it for exo. So here, let's have a quick go. Our reactants will have more energy. Then this is our activation energy. And there's our products with less energy. So this would be an example of exothermic. And from this part to here, that would be the activation energy. Okay, when drawing activation energy, draw an arrow from the reactant line. So always from the reactant line up to the top of the hump. That's how you draw and add your activation energy. And how can we tell if something's exothermic or endothermic? It's endothermic if the products have more energy than the reactants. So this is what I was saying to you before. If the products have got more energy than the reactant. So here the product's got more energy than the reactant, so we know it's endothermic. If the products have got less energy, that should say less. If products have got less energy than the reactants, then we know it's an exothermic reaction. Now, When labeling energy change, draw an arrow from the reactants to the products. Meaning, here's your reactants. You can draw a line straight across. Just do that again. So with a ruler, draw a line across. And there. That is the change in energy in this reaction. Again, you can do the same thing. Just draw a line across. And that is the change in energy in this reaction. And the arrow should go from reactants to products. I've done a double arrow there, which I shouldn't have done. So the arrow should look the way it is on the screen. So hydrocarbons are compounds, and they are compounds that are made of hydrogen and carbon only. So if you get a question in an exam which says, what is a hydrocarbon? Your first mark is saying hydrogen and carbon, and the second mark is saying only. Now, crude oil is a mixture of hydrocarbons found in rocks. And it's made up of animals and living things, plants, organisms that died many, possibly millions of years ago. And the way they died, because they were buried in mud, so there was less oxygen. It means they've decomposed slowly and eventually turned into fossil fuels. Now, crude oil is a mixture. So it's made of hydrocarbons, so it's made of molecules that are only made of hydrogen and carbon, but it's a mixture because each hydrocarbon has a different length in carbons. So the carbon chain is different. So for example, you might have 2 carbon chain, you might have a 6 carbon chain, you might have a 50 carbon chain, a 100 carbon chain. So you've got all of these different molecules or different sizes within crude oil. So crude oil is a complex mixture of hydrocarbons. It contains molecules in which carbon atoms are in chains or rings. It's an important source of useful substances, including fuels and feedstock for the petrochemical industry. So from crude oil, we get things like petrol, diesel, kerosene, fuel oil, lots of different things. The gas that comes out of our stove, all this comes from crude oil. Now the issue is that the crude oil is a mixture. So we need to separate that mixture into individual, what we call fractions. So within crude oil, you'll find petroleum gas, gasoline, naphtha, paraffin, diesel, fuel oil, lubricating oil, bitumen. Each one individually has a use, but as crude oil as a mixture doesn't have as much of a use. So they have to be separated using fractional distillation. Now, when we do normal distillation, it's where we've got a mixture of liquids or we've got salty water, things like that, and we boil it up. So if actually a good example we could look at is here in this flask, we've got water and we've got ethanol. Now, if we heat that up to about 70 degrees, then the ethanol will boil off, leaving the water behind. So what the ethanol will do is evaporate. When it gets to this part here, we have a condenser. The condenser has water flowing through it and water flowing out. So cold water flows through, it cools down the gas here, that turns to a liquid and it drips out the other end. So here, that means here we've got ethanol, and in our original flask, we're left with water, so we've separated them. So using a similar process or thought process in fraction distillation, we can separate all the crude oil into all these individual fractions. So many of the fuels on which we depend for our modern lifestyle, such as petrol, diesel, oil, kerosene, fuel oil, liquefied petroleum gases, all of them come from crude oil. Now, what is fractional distillation? So many useful materials on which modern life depends are produced by the petrochemical industry, such as solvents, lubricants, polymers, detergents. All this stuff comes from the petrochemical industry. The large number of natural and synthetic carbon compounds occur due to the ability of carbon atoms to form families of similar compounds. So if you've got a hydrocarbon that's made of only single bonds, we call that an alkane. If you've got one that's got a double bond, we call that alkene. If we remove this hydrogen just there and we put an OH group, all of a sudden we have an alcohol group. So carbon atoms have this ability to form families of similar compounds. Okay, so how does fractional distillation work? The column is hotter at the bottom than at the top. It's cooler at the top. So the crude oil enters through here, it's been vaporized. Now the whole thing does vaporize except bitumen, which is still a liquid, so that falls to the bottom, and it's siphoned off. Bitumen we use for like roads, things like that. Now, because it's hot vapors, hot gas, it starts to rise. Now, as it rises at different points, because now it's all gas, at different points, different things will condense and turn into liquid. So as the vapors rise, they cool and condense at different levels. Small molecules condense further up, like CH4, C4, H, C4H10. They're small molecules. Then you've got large molecules here where you've got 20 to 50 carbons in the chain or more. So small molecules condense further at the top and the large ones towards the bottom. So for example, these around 250 degrees, diesel will start to condense, turn to a liquid, and it can be siphoned off. At around 120 degrees, naphtha turns to a liquid, it condenses, and it can be siphoned off. So what are the different fractions of crude oil used for? So we use gases for cooking and heating. Petrol's used in cars. Kerosene is used in aircraft. Diesel oil is used in some cars and in trains. Fuel oil is used in large ships and power stations. Okay, properties of fractions. Now, as you can see, we've got less carbons at the top, more carbons at the bottom. So as the number of carbons increases, they become more difficult to ignite. So when it's smaller, it's easier to ignite. It's more difficult to ignite when they get bigger. They are less viscous when they're small. Viscous is like a bottle of water. If I open that bottle of water, and I turn the bottle upside down, all the water will just flow right out. So if I open this up, all the water will just flow right out. If I have a jar of honey and I turn that jar of honey upside down, all the honey will flow out, but slowly. So that means honey is more viscous. So the bigger the molecule, the bigger the more viscous it is. The more thicker it is, the more slowly it flows. So less viscous means it flows easily. More viscous means it doesn't flow as easily. Now, the small ones are more flammable than the large ones, which is a good thing because we use bitumen on the roads. If bitumen was flammable, then we'd have fires across the roads constantly. So bitumen is not very flammable at all because the molecule is so long. Also, as the molecule increases in length, the boiling point also increases. And that's because between each molecule, so if you let's look at this one here, methane. So it's only got one carbon in its chain. So how does one of these molecules attached to another molecule through weak intermolecular bonds. Now let's look at a larger molecule. Let's look at this one. Butane, it's got 4 carbons. How is that going to how are two butane molecules going to attach to each other? Again with intermolecular bonds. But you'll have stronger and more intermolecular bonds. Now intermolecular bonds are weak, so don't get me wrong. They're weak, but the larger molecule has stronger or more of these weak intermolecular bonds. So more heat energy is needed to break this bond than is needed to break this bond. So most of the substances in crude oil are alkanes. Now when we say alkane, we mean something that is a hydrocarbon. So it's made of carbon and hydrogen only, and it follows um, its family follows this rule. CnH2n plus 2. So this is the general formula for all of alkanes. General formula meaning if it's an alkane, it follows this formula. So when we've got 1 carbon, so let's do this. Let's replace N with 1. So C1H 2 times 1 plus 2. So 2 times 1 is 2 plus 2 is 4. So that's C1H4. In other words, CH4. And that's what this is. 1 carbon, 4 hydrogens. So let's see if it works for butane, 4 carbons. So we've got C4H 2 times 4 plus 2. 2 times 4 is 10 plus, sorry, 2 times 4 is 8 plus 2 is 10. So C4H10. So we've got 1, 2, 3, 4 carbons. That's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. That's correct too. So it works. Now, if you're not good with nth term, then what you need to remember is in an alkane, the number of hydrogens is twice the number of carbons plus 2. So look here, we've got 2 carbons, double it plus 2. So 2 times 2 is 4 plus 2 is 6. Yep, we've got 6 hydrogens there. Here we've got 3 carbons, double it plus 2. So 3, double it is 6 plus 2 is 8. How many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7, 8. Yep, so it works. Now, viscosity. So exactly what I was saying before. Viscosity is a measure of how difficult it is for a substance to flow. The higher the viscosity, the thicker it is. So examples of viscous materials include honey, glue, peanut butter. They move, but they don't move very fast. Now, since we're talking about alkenes is something that will come up in topic 10 in more detail, but just so you're aware, now this is only triple. I just want to quickly say this to the triple. C2H4 is ethene. C3H6 is propene. So what's the general formula here? You just double the number of hydrogens. So CnH2n is the general formula for alkenes. But if you're doing combined, you do not need to know about alkenes. Other than there's a small section that you need to know when we do cracking, but that will make sense when we get to it. So this is, again, something I've already explained. We've got a lower boiling point for small molecules and a larger boiling point for the larger molecules. Why does that happen? Because as the size of the molecule increases, the size of the intermolecular force between the molecule also increases. This needs to be memorized. So if a question comes up, it's a quick and easy answer. Now, if the size of the molecule increases and the size of the intermolecular force between the molecule increases, that means more energy is needed to overcome that force, and that means the boiling point is higher. That means the boiling point is higher. So again, I've explained this too. Alkanes are molecules with a general formula CnH2n plus 2. Now, what is a homologous series? Call it homologous if you want, but it's homologous. Compounds in the same homologous series have the same general formula, which is Cn. Well, for alkanes, it's CnH2n plus 2. Now, what's the difference between CH4 to C2H6 to C3H8 to C4H10? The difference is CH2. Each time we're adding CH2. Now, they show a gradual variation in physical properties. So as it gets a lot bigger, they've all got similar chemical properties, and the physical properties change as it gets bigger, as the molecule gets bigger and bigger. So, for example, things like boiling point increase, melting points increase, things like that. And they all have similar chemical properties. So, the larger the molecule gets, regardless of the molecule getting bigger, sorry, the chemical properties will still be similar. Okay, combustion of hydrocarbons. What happens during the combustion of a hydrocarbon fuel? So methane plus oxygen makes carbon dioxide plus water. Now, energy is released during the complete combustion. So this is an exothermic reaction. The carbon and hydrogen in the fuel is oxidized to make carbon dioxide and water. So if you've got a hydrocarbon, you only have carbon and hydrogen. So what are the only two things you can make? If you add oxygen to hydrogen, you're going to get H2O. If you add oxygen to carbon, then you're going to make CO2, carbon dioxide. So you can only make these two products. So if I put here the most randomly named alkane, so whatever we want, and I put ane at the end, and I said there's some new alkane that's been discovered, and I reacted with oxygen. What's the only two things it's going to make? Carbon dioxide and water. By the way, this doesn't exist. I'm just showing you, because sometimes in exam questions they give you randomly sounding things that you've never heard of before. So if they give you a randomly sounding thing and they say, oh, it's an alkane, when it reacts with oxygen or combustion occurs, because combustion means reacting with oxygen, what are the two products? The two products are carbon dioxide and water. Because, and if it says why, it's because it's a hydrocarbon. And what's a hydrocarbon? It's a molecule that is made of only, it's carbon and hydrogen only. So it can only make carbon dioxide and water. So here we've got methane plus oxygen makes carbon dioxide and water. Ethane plus oxygen makes carbon dioxide and water. Propane and oxygen makes carbon dioxide and water. Butane and oxygen makes carbon dioxide and water. So if a question like this comes up, there's no excuses. We know exactly what it makes. Okay, now, if we look at the symbol equation for combustion, one of these is incorrect. So I want you to identify which one is incorrect and write down the correct symbol equation for it. If you're not able to write down the correct symbol equation for it, even if you just tell me which one is incorrect, 1, 2, 3, or 4. So out of these symbol equations, which one is incorrect? Okay, so one said number 1, it's not number 1. Number 1 is correct because that is CH4. Good. It's number 2 that's incorrect because we're talking about ethane. Ethane is not CH4. It is C2H6. And if we react it with oxygen, we do indeed get carbon dioxide plus water. Okay, but let's balance this now. We've got two carbons here. So that means we have to have two CO2 here. Excellent. Because this is a question that can come up in an exam. So it's important to understand. Now, balancing equations is just something that many students struggle with. So I'm just using this as an example to go through balancing equation at the same time. Now here, we've got 6 hydrogens. How many water molecules can we make from 6 hydrogens? We can make 3. Because what's 3 times H2? 6 hydrogens. Now, altogether, we need to balance the oxygens now. So we've got 2 times O2, which is 4 oxygens. And here we've got 3 times 1 oxygen, so that's 3 oxygens. That's 7 oxygens altogether. Now, if we're talking about O2, then we would divide 7. So that means we need 3.5 oxygens. Now, when you're doing combustion, you can write your answer as halves. It's not a problem. You can write 3.5 oxygens, or you can just double the whole thing. That's what's happened here. That's why we've ended with 13 oxygens, because the whole thing's been doubled. So if we were to double everything, then we would have 2 C2H6 and one person's already given me the answer. Excellent, well done. That's correct. Plus 7O2 becomes 4CO2 plus 6H2O. So let's move on to the next part. Now, I'm aware I'm not asking too many questions because in the AMALathon it is more about just getting your understanding right. So I will still ask a few questions, and when I do, I hope I get lots and lots of answers. But the main thing is for your understanding to be 100% correct. So please keep asking lots of questions. Don't let me move on. Don't let me move on if you've not fully understood. So now what we're looking at is incomplete combustion. So what happens when there's a lack of oxygen? Now, when there's lots of oxygen, then if you've got CH4, then the hydrogens are going to react with the oxygen to make H2O. The carbon's going to react with oxygen to make CO2. But when there's not enough oxygen, what happens instead is that carbon might only have, instead of 2 oxygens, it might only react with 1. So carbon monoxide is made. If there's not enough oxygen at all, the carbon might be left by itself. So we end up with carbon monoxide, or we end up with carbon particulates, as in just carbon soot. So if anyone's ever seen a chimney, that kind of the black powder that comes out of the chimney, that's soot. Or even in a fire, when you have a barbecue, for example, and you know the coals that you use at the end, and if you put your finger across one of the coals when it's cooled down, you get this black residue. That's soot. Now, what are the problems of carbon monoxide? Number one, it's not easily detected as it's colorless and odorless. That's why in our homes, it's important to have carbon monoxide detectors, particularly around um, our boilers. So carbon monoxide is a toxic gas. It binds to the hemoglobin in red blood cells. So red blood cells don't have a nucleus. Instead, they have hemoglobin, which is an iron molecule surrounded by 4 protein groups. So iron molecule, and they attach to oxygen. Now the problem with carbon monoxide is instead of the oxygen attaching, the carbon monoxide attaches. Now, whereas the body, so whereas within the body, the red blood cell releases the oxygens wherever the body is oxygen deficient. So if it goes past the respiring cell, the oxygen will enter the respiring cell. But carbon monoxide attaches irreversibly to the red blood cell. Because it attaches irreversibly, it means the only way to get that red blood cell to work now is to destroy it and for the body to make a new one. So if a person breathes in too much carbon monoxide during a fire or something like that, it means they suffocate. They don't initially feel like they're suffocating, still breathing in. So it reduces the oxygen content in the blood. Very dangerous and toxic chemical. Then we've got carbon particulates. That's just carbon by itself. They cause global dimming, meaning they can enter the atmosphere and they reduce the sunlight, and also health problems for humans. So if when we breathe carbon particulates in, they they cause damage to our respiratory system, as in our lungs. Okay, sulfur dioxide. Now, every lump of coal predominantly is full of carbon. But within that carbon, there is a little bit of sulfur. Now, when that carbon burns, it turns into carbon dioxide, which has its own issues, global warming, etc. But when the sulfur burns, it turns into sulfur dioxide. So when the fuel burns, the sulfur reacts with oxygen to make sulfur dioxide. The sulfur dioxide dissolves in water and causes acid rain. So when you've got a cloud, that cloud is full of H2O molecules. Oops. Now the process is a little bit more complicated than what I'm showing, but anyone that's doing A-level chemistry will learn about that more complicated process in more detail. But this is enough for the time being. So what happens now is, if the sulfur dissolves into one of these raindrops, it becomes acidic. So some of these raindrops will be acidic. Not every single one, just a few. Wherever a sulfur dioxide molecule reacts with that rain. Now that means that those drops will contain acid, specifically sulfuric acid. So hence we now have acid rain. So some fuels, we've already mentioned this. So the issue with sulfur dioxide and acid rain is it causes respiratory problems. Also, if it gathers within a lake, so can you imagine you have a lake full of water and within it, when it rains, you start to get small amounts of acid. Now, over time, the water evaporates, but the acid part doesn't evaporate. So every time it rains, the acidity accumulates. And over time, this causes harm to the aquatic creatures. The same thing with the trees around that area, or if you've got soil that takes in a lot of acid rain, it causes, it makes it more difficult for the trees to grow. So what effect does acid rain have on the environment? It damages buildings. So if you've got, in particular, if you've got something made of calcium carbonate. So a lot of old statues were made of limestone, calcium carbonate. And when slowly, every time it rains, each time a certain number of molecules, certain number of molecules will react with the sulfuric acid, releasing carbon dioxide gas, causing it to break down. So long term, it causes damage to buildings. It damages plants because some plants don't grow well in acidic soil, and it lowers the pH of ponds and lakes because of what I mentioned in the previous slide. The water evaporates off, causing the acid part to accumulate within the lake or the pond. And because you don't have a flow of water, it just accumulates. Oxides of nitrogen. How is sulfur dioxide produced during the combustion of fuels? So the conditions in a car's engine is very hot and they're very hot and it's high pressure. Now, when we say very hot, it can reach temperatures of 2000 degrees. That causes the nitrogen in the air to react with oxygen, forming oxides of nitrogen. Now, nitrogen, I'm actually going to recap this really quickly because it's from topic 1. And don't forget, topic one is really important for, well, it's one of the topics you need to know for paper two. So if anyone needs to recap it on the AMALearning YouTube channel, in the live section, there's the first 3 days of chemistry recordings are all topic one because it is a significantly big topic and it is very, very important. Now, nitrogen is in group 5. That means nitrogen has 5 electrons in its outside shell. Now, if it's got 5 electrons in its outside shell, it needs 3 more. So that's how many we share. 1, 2, 3. Now, if it's got 3 being shared in the middle as part of a covalent bond, it had 5 initially, it shared 3, it's still got 2 more electrons. So they go in the outer shell, outer part, the part that's not being shared. And it's the same thing for our nitrogen here. Nitrogen's going to share 3 electrons because it's got 5 electrons, it wants 3 more. So we put 3 in the middle and there's 2 electrons left to go in the outer shell, in the rest of the shell. So that's your covalent bond. There's 6 electrons. Now, 2 electrons means 1 covalent bond because a pair of 6 electrons are being shared. So it's 3 covalent bonds. So 1, 2, 3. That's a triple covalent bond is very strong. To break that bond takes a high amount of energy. In other words, 2000 degrees or lightning. So whenever there's thunder and lightning, some of you may have noticed a certain smell in the air. That smell in the air is nitrogen being broken apart and then attaching to oxygen to make NO2 or NO. So the oxides of nitrogen. Now, they also, like sulfuric acid, dissolve in the rain to make acid rain, and they cause respiratory problems. Okay, how is hydrogen fuel made? Now, hydrogen can be made in a number of ways, including reaction of methane from natural gas with steam. So if you get methane and steam, it releases hydrogen gas. Also, when you do the cracking of crude oil, so when you crack crude oil, um, it also makes hydrogen gas. Or you can do the electrolysis of water, which splits H2O water into H plus and OH minus. And when the H plus goes to the cathode, two H pluses gain electrons from the cathode and become hydrogen. It's a really good question just been asked. In paper 2, chemistry for combined, how many marks for calculations and bonding? Now, for bonding, I can't guarantee a certain number of marks, but for calculations, 20% of your exam will be calculations, minimum. Okay, so all chemistry exams are around 20%. So you need to make sure you revise. So you need to make sure that you revise, what do you call it, make sure you revise the calculation stuff in detail. Okay, so hydrogen fuels. So really good, before we just continue, it's a really good question. It says, Why do we do electrolysis with a covalent bond? That's a really good question. Um, because what electrolysis does, it provides the energy to break the covalent bond between the H plus and OH minus. As into, so that initially you do have a covalent, you have, so there, what you've initially got is H2O, and you've got a covalent bond. The electricity provides enough energy to break them apart. And what actually happens is the oxygen takes when you've got your electrons, the oxygen takes the electrons, which is why it becomes negative. But again, you don't need to know that part until you get to A level. Okay, so advantages and disadvantages of hydrogen fuel. It's easy to ignite. Lots of energy is released per kilogram. Water is the only product of combustion. It's not a finite resource. Now, a disadvantage, there's not many hydrogen filling stations. In fact, it's unlikely anyone that's currently that's watching this has ever seen um, a hydrogen fuel station. They are not common. And it can be difficult to run a hydrogen fuel car depending on where a person lives. Okay, cracking. So cracking is where you take a large hydrocarbon, which is not particularly useful, and you break it down or crack it to make smaller, more useful molecules. Now there's two different types of cracking. There's catalytic cracking and there's steam cracking. So this comes up as a question. Catalytic cracking has requires a high temperature. They both need high temperatures. The only difference is catalytic cracking requires a catalyst and steam cracking requires steam. Simple as that. Now, what actually is made, there's a small mistake here. There's one small alkane that gets made, butane. This is not hexane, this is hexene. So two small alkenes are made. Now, when you crack something, so we've got here dodecane, 12 carbons. Whatever you make, there has to be conservation of mass, conservation of atoms. So you have to end up with the same number of carbons and the same number of hydrogens as you started with. So let's look at an example. Let's use C6H14. Now, whenever you crack a large molecule, it will always make an alkane and an alkene. So C6H14 makes an alkane and an alkene. So let's say it makes an alkane, which is C2H6. So what else is it going to make? Now we had 6 carbons, we've used up 2. How many carbons are left? 4. How many hydrogens are left? 14 take away 6, 8. Now whenever you double the number of carbons to get hydrogens, that's an alkene. So we know that's an alkene. Now we know from our general formula before, C2H2n plus 2, that's an alkane. So we always make an alkane and an alkene. Now it's important, cracking is important because it takes large molecules which, so actually let me start again. So small alkanes such as petrol, there's now probably over 1 billion cars around the world. And the amount of petrol coming out the ground is not enough to fulfill the demand of petrol. So what they have to do is use a larger molecule, larger alkane, which doesn't have as big a demand, and crack it to make more petrol. So smaller alkanes are useful as fuels, but smaller alkenes are used to produce polymers and are starting materials for production of many other chemicals. And that's something I'll go into more detail when we do topic. C9, which is triple only. So, this is now the second part of topic 8, which is Earth and atmospheric science. So the first part was fuels and earth science, and the second part of topic 8 is Earth and the atmospheric science. So the Earth, sorry, let me repeat that. So my voice is still not fully recovered. The Earth and atmospheric science. Which, if you learn it like a story, it makes it a lot easier to memorize. And when this comes up as a 6-mark question, which it sometimes does, if you write the story down of how the Earth went through all these processes, that's sufficient. Of course, no one lived 4.6 billion years ago, so the evidence is very limited, and there's no guarantee that that's exactly what's happened. And of the some of what we're about to go through is a bit far-fetched, particularly how things came from nothing all of a sudden. So you just got to memorize it as a story, it's like a made-up bedtime story that you can then answer any question with. So, volcanic activity. How did the Earth's atmosphere form? So, these theories about the Earth's atmosphere have changed over time. Um, you could say that the theories have evolved, just like the theory of evolution. It's evolved over the years as well. Evidence is very limited because of the time scale of 4.6 billion years ago. So, there's no 100% guarantee that the Earth was 4.6 billion years old in the first place. So to even know what happened more than 4.6 billion years ago is impossible. So this is based on whatever evidence can be garnered. So one theory suggests that during the first billion years there was lots of volcanic activity. The nitrogen is unreactive and built up over time. So when this volcano, the the initial surface of the Earth erupted, it released ammonia, methane, nitrogen, carbon dioxide, and water vapor, and no oxygen. Oxygen was part of the carbon dioxide and part of the water vapor, but not by itself. So ammonia was released, which is NH3. Methane was released, which is CH4. Nitrogen, which is N2. Carbon dioxide, CO2, and water, which is H2O. Now, if you look at this logically, we're saying the Earth's really hot. Underneath the surface, it's very hot. All the rock is melting. So you've got lots and lots of magma. And the magma has to be released. So it's released through the volcanoes. So very volatile. Lots of gases being released through the crust. Now, over time, the crust is going to start cooling down. And as soon as it cools down, what's the first thing that's going to happen? If you look at all the different gases that are available there. Now, oxygen remains a gas up until minus 200. Carbon dioxide as well. All the other gases, they don't turn into a liquid anytime soon, as it's within the negatives, negative 100 and smaller. So the only one that's going to be able to turn into a gas is water vapor. So as soon as the Earth got to around 100 degrees and cooled below 100 degrees, the water vapor started to condense. It rained, it formed oceans. The atmosphere would have then mostly consisted of carbon dioxide. So the atmosphere was mainly carbon dioxide. What mainly came out of volcanoes was the water and the carbon dioxide. The water cooled and made the oceans, which have then slowly broken through the rock. And the atmosphere was left with carbon dioxide. Now the carbon dioxide level started to fall because carbon dioxide dissolves into the oceans. Carbonates in the water precipitated, making sediments. So that means the water would have had to have other things inside it that would have come from the rocks, and then the carbon dioxide has reacted with those to make carbonates. So the carbon in this respect has become locked in the rocks. For example, calcium carbonate. So if it reacted with any calcium in the water, we would have made calcium carbonate. So now some of the carbon has been locked in the rocks. So the carbon dioxide level started to decrease slightly. Now the early atmosphere, there was zero oxygen. Now we've got 20%. Early atmosphere, most of the atmosphere would have been carbon dioxide. This is ignoring water. And now we've got trace amounts, about 0.04% of the Earth's atmosphere. So what happened to the proportion of carbon dioxide and on oxygen? So when the amount of oxygen increased, animals began to evolve also. Now, as the level of water increased, as in the oceans increased, sorry, that took in a lot of the carbon dioxide from the atmosphere. Anything that was green inside the water. Now, the question that would need to be asked here is where the green stuff came from in the first place. Um, because just before this, nothing was able to survive because of how hot it was and all the volcanic activity. Then the water has fallen to the earth, and then all of a sudden we've got algae now. But again, like I said, you've got to understand it like a story. So now we've got lots of algae. They produce oxygen around 2.7 billion years ago. So the algae photosynthesized, they start to take the carbon dioxide in and release oxygen. So the algae took CO2 in and released oxygen, which means over the next billion years or so, plants started to evolve. And they also took in carbon dioxide and released oxygen. So as the oxygen levels start to increase, animals that survived using oxygen began to evolve and spawn out of nowhere also. So carbon dioxide plus water. So during photosynthesis, carbon dioxide was taken in by the plants, and that created glucose and oxygen. Oxygen was produced by photosynthesis, and so its proportion increased within the atmosphere. There should be a number 6 just here, 602. Okay, now, why did the carbon dioxide decrease? We need to be able to answer this question also. We need to be able to say, what were the original gases? How were the oceans formed? When the oceans were formed, why did the carbon dioxide level decrease? Because it dissolved inside. Why did carbon dioxide levels decrease and oxygen levels increase? That's where you talk about the evolution of plants, etc. And you also then individually need to know why carbon dioxide decreased. Because the evolution of algae and plants, which photosynthesized, took in carbon dioxide and released oxygen. Some dissolved in the oceans and became locked in rocks. So initially, when the oceans formed, the carbon dioxide reacted with some of the metals in the water to make carbonates, and some became locked in fossil fuels. So what that means is when organisms started to die over many years, so for when an organism grows, it locks carbon within itself. So when a tree grows, it takes carbon dioxide from the air, and then that tree becomes part of the amino acids that make the proteins that help it grow. Same with human beings, same with other animals. The protein part of it is initially comes from carbon dioxide. When a plant makes carbon dioxide, if you add a nitrate group to it, you've made an amino acid. Join those amino acids together, and you now have a protein. So that carbon was locked in organisms, which has then, over millions of years, or billions of years according to this, have then become turned into fossil fuels. Okay, so how can we test for oxygen? Insert a glowing splint. Now, glowing means that you have set it alight and then blown it out. So you've got embers only. So you insert a glowing splint into the test tube. If it is oxygen, it will relight. Okay, greenhouse effect. So this initial bit, learn it like a story. Volcanic activity released lots of gases. When the temperature went below 100 degrees, water vapor condensed and it formed the oceans. The carbon dioxide dissolved in the oceans and the carbon dioxide was locked in rocks because it reacted with things to make carbonates. Then, because there was lots of carbon dioxide in the water, things like algae evolved, plants evolved. They took in the carbon dioxide and they released oxygen. So carbon dioxide levels decreased massively. So the carbon dioxide now has been locked in, was decreased because of the plants and algae, because they photosynthesized. It got locked in rocks and it got locked in fossil fuels. And then you need to know the test for oxygen. Okay, so what is climate change? Climate change is the changes to the Earth's average temperature. Greenhouse gases are gases that contribute towards climate change. So, for example, carbon dioxide, methane, and water vapor. These molecules are a concern. So, mainly carbon dioxide is a concern because they can stay in the air for years or even centuries. Water vapor is not as big a concern, and methane to some extent as well, because it doesn't linger in the air for as long. They're not a huge concern because the molecules only stay in the air for a few days. Water vapor a few days, methane can be for a few years. Carbon dioxide lasts for a lot longer. Okay, now what is the greenhouse effect? The greenhouse effect traps some of the energy from the sun and keeps our planet at a suitable temperature for life. So it's actually a process that we require. So if this is the Earth, when the sun's energy hits the surface and comes back out, it's absorbed by this carbon dioxide layer. And when that carbon dioxide absorbs the energy, it then emits it out in every single direction. So some of it then goes back towards the surface. Now, shorter wavelength radiation from the sun, it passes through the atmosphere no problem. When it's absorbed by the surface of the Earth, it is re-emitted from the Earth's surface as longer wavelength radiation. That longer wavelength radiation is absorbed by the greenhouse gases. So it then re-emits some of that energy back towards the Earth. Now that causes an increase in temperature by about 2 or 3 degrees. If we didn't have that 2 or 3 degrees, then we'd be in some parts of the world would be in an ice age. The issue now is that all the carbon dioxide that we just said has been locked in the rocks and locked in fossil fuels. We're now burning these fossil fuels and we are releasing that carbon dioxide back into the atmosphere. So rather than it being an increase of 2 or 3 degrees, we've gone beyond that point. And which is why we're seeing lots of changes in weather patterns. So the concentration of carbon dioxide in the atmosphere has increased over the last couple of years, or not couple, many last few years. There's a correlation between increase in carbon dioxide levels and global temperature. So what you're seeing here is global temperatures increasing and carbon dioxide levels are increasing. But you can also see it's a bit of a zigzag. It's going up and down. And it's because of that you get some people who have other ideas. Okay, so what proportion of these other gases are in the atmosphere now? So nitrogen is about 78% because nitrogen is unreactive. It's the unreactive element. As I explained to you before, breaking that triple bond is difficult. Oxygen is about 21% and the remainder of gases are make up around just over 1%. So for 200 million years, the proportions of different gases in the atmosphere have been pretty much as they are today. Now, carbon dioxide makes up about 0.04%, but if you go back 20, 30 years, it was about 0.03%. Argon makes up about 0.9%, which is a noble gas. Now, why has carbon dioxide increased? Mainly because of increased combustion and deforestation. Because we're burning a lot more fossil fuels. That's what combustion is. Combustion is when we react a fuel with oxygen. And methane, because there's a lot more waste and increased in agriculture. So we throw our waste food away, microorganisms break it down and they release methane, CH4, and increase agriculture. So we've done a lot of deforestation and we've replaced it with farms for cows and things like that. So that has led to, again, an increase in methane gas being released. Now, what are the consequences of global climate change? So the polar ice caps are melting. Organisms that live on the ice are losing their habitat. So things like polar bears, etc., are struggling to survive. They say polar bears will be extinct by 2050. Now, if all that extra ice is melting, that means the sea levels rise. Not just because of the extra water, also because if the world is becoming warmer, if the world becomes warmer and the oceans become warmer, the water will expand. Warm water expands. Same way if you're boiling some water in a pan, what happens? The water rises because as it gets more and more energy, it expands. It takes up more space. That's why we've had increase in flooding. If you think about how many floods we've had over the last year or so, it's because of this. Now, areas that were flooded with seawater now have saltier soil, so things won't grow as well there. So now habitats are destroyed. So everything has a knock-on effect. Then we've got a change in extreme weather. Extreme weathers become more frequent. That can be more storms, which is what's happening, more floods, and that also destroys habitats. And it changes migration patterns. So organisms such as birds or insects change their migration patterns. They might migrate later, earlier, or migrate somewhere else. And that can disrupt food chains. So that's something that's happening now as well. Only recently there's something in the news about a bird that hasn't been seen in the UK for many, many years. Extinction. Different plants and animals are at risk of extinction. Some scientists predict that by 2050, 30% of plants and animals could be at risk. So warmer sands is causing more turtles to be born female. And also because of rising sea levels, turtles have got less nesting sites. Changes to rainfall. So some areas now have heavier rainfall and become wetter. This destroys habitats because they're now flooded areas. And this habitats, more land is becoming desert in some other parts because it's become really hot there. Some areas have less rainfall and become drier. And now you might be thinking when it's warmer, why are we having more rainfall? Because when it's warmer, more of the water from the rivers and the lakes, etc., goes into the sky. So we end up with more clouds and more rain. And here's what I was explaining to you just a bit ago. Seawater will expand. When water's warmed, it expands. Warmer water will mean that the water will have a greater volume. So that means not only do we have more water because the ice caps are melting, we also have water that's expanded, so it's taking up more space. This can cause flooding and destroy habitats. Okay, last slide, carbon footprint. So what is carbon footprint first? Is the total amount of carbon dioxide and other greenhouse gases emitted over a full life cycle of a product, service, or event. So if we're talking about our carbon footprint, it's how much carbon dioxide and other greenhouse gases we emit because of our activities on a yearly basis. So the carbon footprint can be reduced by reducing carbon dioxide and methane emissions. So for example, we could use solar panels to produce electricity, use a bike instead of a car to travel, improve our home insulation. Okay, so testing ions. The test for any ion must be unique, so that we can use the results to identify the ion that is present. So if two ions produce the same result, you wouldn't know for sure which ion you had. So you know all the tests that we're about to go through, you need to memorize them. So that if you were given an unknown substance, you can work out what the unknown substance is. It's actually once you've understood it, it makes it so much easier as a topic. So the first type of test that we need to be familiar with is flame tests. And again, you need to memorize what the test is and you need to memorize the positive results. So the flame test is a test that involves the use of a Bunsen burner to identify some metal ions. So you get a nichrome wire, you dip it into your metal ion, that is, and depending on what color you see, it tells you what metal it is. So if you see a crimson red, as in if the flame becomes a crimson red, then you know it's lithium. Yellow flame is sodium, lilac flame is potassium, orangey red flame is calcium, and green flame is copper. So you just need to, there's no other way of doing this other than memorizing it. Now there are limitations with the flame test. If a sample contains a mixture of ions, that then some of the flame colors can be masked, and so it can be very difficult to identify them. So for example, if you've got a bit of sodium and a bit of lithium, you're going to see more of the red from the crimson red flame than the yellow. So you might not realize there's more than one ion there. The other issue that can happen is sometimes the nichrome wire is not cleaned between use. Now the best way to clean it is by putting it into acid. Dip it into an hydrochloric acid, then all the excess metal ions react with the acid. Because what does the metal and acid give us? I'll use HCl as an example. It gives us a salt, so metal chloride, plus hydrogen gas. So the second it starts bubbling, so when you stop seeing hydrogen bubbles, you know that all the metal has reacted out. But if someone just dips it in and dips it out, quick dip in and they think, oh, I'm done, it's clean. That means it's possible that some metal might still be on the nichrome wire. Okay, this is now another test. You can identify metal ions by using sodium hydroxide. So you add the metal ion into a test tube. Then you add sodium hydroxide in excess. Then you observe the color of the precipitate formed. And you use the color to identify the metal ion. So if it's aluminium, calcium, or magnesium, it forms a white precipitate. Now you're probably thinking that that's not very useful. But with aluminium, if you keep adding more and more sodium hydroxide, eventually it dissolves so that we can work out which one's aluminium. But with calcium and magnesium, they both form white precipitates. Now, if we go back to our flame test, calcium produces the orangey red flame and magnesium produces a bright white light when it gets burnt. So you can still identify which one's which using flame tests. Then copper 2 is a blue precipitate. Think copper 2 sulfate. When in school, when you made copper sulfate crystals, they were a bluish color. Iron 2 leads to a green precipitate. Iron 3 makes a brown precipitate. Now, that's two tests for metal ions. You also need to know the test for non-metal ions. So how can we test for ammonium ions? And ammonium ions are NH4+. So to test for ammonium ions, now this is a positive ion, but actually it's a non-metal. But it still comes under the category of positive ions. So this comes in the same category as your metal ions, because group 1 ions give us positive 1 ions. Group 2 metals group 1 metals give us metal plus, group 2 metals give us metal 2 plus, and group 3 is, for example, aluminium is group 3 would be aluminium 3 plus or metal 3 plus, just keep it consistent with the previous ones. So from group 1, you might have lithium plus. From group 2, you might have calcium 2 plus. And then you've got aluminium 3 plus from group 3. NH4 plus is an example of a non-metal that produces a positive ion. So you'd add sodium hydroxide, then you warm the mixture. Now, if ammonia gas would be given off if ammonium ions are present. So this is just explaining how you would tell the difference between aluminium, calcium, and magnesium, which I explained in the previous slide. Now, ammonia, like chlorine, well, the opposite to chlorine. With chlorine, when you dip damp litmus paper, it turns red and then turns white. But with ammonia, it needs to be damp litmus. Now, why is it damp litmus? Because that way the ammonia gas can dissolve into the damp liquid. Ammonia will not dissolve on paper because it's a gas. But if it's damp, it will dissolve into the liquid, the water that you've dampened it with, and it will dissolve in, and then it will turn the paper blue because ammonia is an alkali. So that's how positive ions done. And in positive ions, we looked at two different tests. Now, what were the two different tests? Flame tests and also adding sodium hydroxide. And from that, we can identify a majority of metals. Now, how can we test for negative ions now? So one is testing for carbonates. So carbonates are CO3 2 minus. So that's a negative ion. Now, if we have, for example, calcium carbonate, which is a metal carbonate, and if we think back to what we learned in our acids and alkali topic, when you add an acid to it, for example, HCl, what does it give us? It gives us calcium chloride, which is a salt. I'm not going to balance this. It gives us water, and it also provides us with carbon dioxide. Now, how do we know? How can we test for carbon dioxide? We use lime water. The lime water turns cloudy when you bubble carbon dioxide through it. Now, if we have a substance, an unknown substance, we add it to acid, we bubble the gas that it produces through lime water. If the lime water turns to a white color, what does that tell us? That is carbon dioxide gas, and therefore it must be a carbonate. So whatever we've just tested must contain carbonate, CO3 2 minus. So if we have an unknown substance, we add it to an acid. The gas that's produced, we bubble it through lime water. Lime water turns white, and that shows us that it's a carbonate. Now, how can we identify sulfates? Sulfates are SO4 2 minus. So what we would do here, we add hydrochloric acid, then we add barium chloride. If a white precipitate is made, then it contains sulfate. So simple as that. You add your unknown substance, then you add hydrochloric acid, you add barium chloride, and if it turns white, it's SO4 2 minus. And our third test for testing negative ions is we get our unknown substance, we add dilute nitric acid, which is HNO3. We add silver nitrate, which is AgNO3. Now, if it turns white, then it means whatever you're testing is a chloride, as in it has a Cl minus ion added to it. Cream means a bromide, so it's got Br minus, and yellow means it's got iodine, so I minus. So if you now take your two positive ion tests, which were flame tests and adding sodium hydroxide, and then add it to our 3 tests for carbonates, CO3 2 minus, our test for sulfates, SO4 2 minus, and then this test to identify group 7 halides, we can identify overall substances. So here, this is really good slide because it summarizes all the negative ion tests. So carbonates, we add dilute acid and bubble through lime water. Positive result is that lime water turns cloudy. We therefore know it is CO3 2 minus. If we add hydrochloric acid and barium chloride, it becomes white. Then we know it's SO4 2 minus. So I'm writing it again because it's just a bit more clear than the way I wrote it there. And then if you add dilute nitric acid and silver nitrate, it turns white, it's Cl minus, cream, it's bromide, Br minus, and yellow means it becomes I minus. Okay, now let's practice identifying an unknown ion. So you could test for a metal ion by taking a sample and adding sodium hydroxide. Or you could do a flame test. That would indicate to you what metal is inside the compound. Then you do your other 3 tests, and that would indicate to you if it's a carbonate, a halide, or a sulfate. And then overall, you'll have the positive ion and the negative ion, so you know the overall compound that you're trying to identify. Okay, so let's try this question. We've got in fact, I'm going to talk through it, but I want you to have a go at it while I'm talking through it. So we've said from a flame test, we had no color. But when we added sodium hydroxide, it's become green. So when we add sodium hydroxide, let's quickly go back. What does green identify it as? Okay, it's just there. Green means it's Fe2 plus. Okay, so we now know we've got Fe2 plus. So in X, for X, we know we've got Fe2 plus. Now, adding nitric acid and silver nitrate, we had no reaction. So it's not a halide, but adding hydrochloric acid and barium chloride gives a white precipitate. Now, what does that experiment tell us? Hydrochloric acid and barium, sulfate. So that's SO4 2 minus. So we've got Fe2 plus and we've got SO4 2 minus. So what's our overall compound? It's FeSO4. Okay, so if you can give me Y now, I'm going to just pause. I'm going to give you a small amount of time. Okay, so a flame test, let's look at Y now. If it gives a yellow flame, that indicates that it's sodium, Na plus. When we get a yellow precipitate by adding nitric acid and silver nitrate, that means it is, let's quickly have a look. Yellow precipitate is iodine, it says iodide. So it's going to be sodium plus and I minus, so it's going to be NaI. Now let's look at Z. Sodium hydroxide gave us a brown precipitate. So thank you to those that gave me correct answers. Well done. They were all correct. So that would be Fe3 plus. And here a cream precipitate would mean it's Br minus. So that would give us FeBr3. And we've got them all right. Iron 2 sulfate, sodium iodide, iron 3 bromide. So we've got FeSO4, NaI, and we've got FeBr3. Now, what are the advantages of using instruments instead? So all the experiments that we've just discussed, they all rely on, on our interpretation. So a person might confuse yellow with cream, for example. Someone might confuse orangey red with crimson red. So instrumental methods are more accurate, they're more sensitive, and they are much, much faster. So an instrumental analysis is the use of equipment to carry out an analysis of chemicals and detect elements and compounds. So we're using actual equipment and the equipment does the analysis for us. So it's more accurate, it's more sensitive, it's fast. Now, instrumental analysis is also automatic, it's precise, and you only need a small amount of the substance. Okay, now what does it mean if apparatus is more accurate, precise, more sensitive? So these are keywords that will benefit if you have an understanding of the difference between the three. If it's precise, it means the values obtained are close to each other. If it's sensitive, it means it can detect small amounts of substance in a small sample. If it's accurate, the values obtained are close to the true value. So precise and accurate are different things. Precise means the values obtained are close to each other. That doesn't necessarily mean that they're accurate. Accurate are the ones that are values that the values obtained are close to the true value. So if you look at this is low precision, low accuracy. We know it's low precision because they're not close to each other. We know it's low accuracy because this one is close to the target, but the rest aren't. This is high precision because everything is close by. It's all in the same area, but it's not accurate as it hasn't hit that middle spot. This is highly accurate because it's quite close, but the precision is not as high because the spots are far from each other. Here you've got high precision, high accuracy because you've hit that central point and all the points are close to each other. Okay, flame photometer. So if a sample is put, so flame emission spectroscopy. So this is the technological way of doing a flame test. So flame emission spectroscopy is an example of an instrumental method used to analyze metal ions in solution. So this tells us if the sample has what positive metal ion it has inside the sample. So the sample is put into a flame. Same way we do a flame test. Now, instead of us detecting the light and working out what color it is, the light given out, because it has a certain wavelength and certain frequency, is passed through a spectroscope. Now, a spectroscope takes the light's wavelength and based on the wavelength gives a color. So the output is a line spectrum that can be analyzed to identify the metal ions in the solution and measure their concentrations. This can detect much smaller quantities than other methods. So this is um, what the line emissions look like. So you can see what calcium 2 plus looks like, copper 2 plus, potassium 2 plus, lithium plus sodium plus, and then this is a mixture of two metals. So what we need to do in this, looking at this line emission is, these line emissions is to say, from the sample below, looking at the line emissions, find out what the mixture of two metals actually is. So if we look at this, what can we see? We can see lithium, because I'm going to highlight it. So you can see that line, actually that's way too wide. Yeah, well done. It's a mixture of sodium and lithium, and you can see that in the lines. So I'm just going to show, if no one's noticed it yet, that lithium line there is the same as that lithium. Whoops. The lithium line here is the same as the lithium line there. That line overlaps. This line overlaps. This one, and this one. So it definitely has got lithium. Now, if you look at the remaining lines that are left, it's exactly the same as sodium. So look, that central area there is the central area there. These two lines are also them two lines there. So it is a mixture of sodium and lithium. So it gives you much more accurate data. Okay, let's move on to alkanes. So a group of molecules with the general formula CnH2n plus 2. So this is alkanes, is something that we've already covered. And we've already covered the fact that they have the general formula CnH2n plus 2. They're all part of the same homologous series. They all have similar chemical properties. And the physical properties vary gradually due to differing sizes. Now, how can alkanes be identified? They're fully saturated with hydrogen-carbon covalent bonds. So that makes them very unreactive in terms of um, that makes them quite unreactive. So if you, for example, got a um, bromine bond, there's no room for these bromines to attach, so they wouldn't attach. Now, when we draw these, if, for example, we're drawing ethane, meth means one carbon, eth means two carbons, prop means three carbons, and bute means four carbons. Ane means it only has single bonds. It's completely saturated. So if I say draw, let's start with ethane. Ethane means it's going to be two carbons and it only has single bonds. So the first thing you do is draw your two carbons. Now each carbon can have four bonds altogether. So this carbon here already has one bond. So let's add number 2, 3, and 4. Now they're hydrocarbons, which means it's only made of hydrogen and carbon. So all these additional bonds are hydrogen. This carbon here now has one bond. There's number 2, number 3, and number 4. Well, we've drawn ethane. Now if we're drawing pentane, pentane's got five carbons. So we add our five carbons first. 1, 2, 3, 4, 5. Now this carbon's already got one bond. So there's number 2, number 3, number 4. This carbon in the middle already has two bonds. So there's number 3 and number 4. This carbon already has two bonds. So there's number 3 and number 4. 3 and number 4 and 1. This last one already has one. Number 2, number 3, and number 4. And then all these are going to be hydrogens because it's a hydrocarbon, and hydrocarbons are made of carbon and hydrogen only. Okay, so these should be written like this: CH4, C2H6, so this should be subscript. Okay, alkenes. Alkenes follow the general formula CnH2n. So however many carbons we have, we double them. And the difference is it has a carbon double bond, as you can see here. So this time the functional group is the double bond. Now the reactions of alkenes are determined by the functional group. And what happens is, if you've got carbon-carbon double bond, is that the double bond breaks. Now, if the double bond is broken, how many more bonds can that carbon now make? It can make an additional bond here, and it can make an additional bond here. So it can make these two extra bonds. So when alkenes react, the carbon-carbon double bond breaks and becomes a single carbon bond. What that means is it can then react with other chemicals. So this is essentially what happens. I'll show you here. We've got ethene. Now, along comes hydrogen. This double bond breaks. So now we have each of these carbons only has 3 bonds. So now one extra bond can form here where this hydrogen attaches, and another bond can form here where this hydrogen attaches. So we've just gone from ethene to ethane. So this shows it here as well. An alkene plus hydrogen becomes alkane. The carbon-carbon double bond breaks and becomes a single carbon-carbon bond, which means it can now attach itself to 2 more elements. Same thing happens with bromine. That double bond breaks, so one bromine attaches here, one bromine attaches here. Now, bromine is a good example of proving if something's an alkane or alkene. Now, if it's an alkene, alkenes react with halogens. So they'll react with Cl2, Br2, I2, because they'll break the double bond and they'll attach to both of the halogens. So alkenes are more reactive than alkanes. They react with bromine water and turn it colorless. And so this can be used as a test for alkenes. So the way you've got to understand this is when you put an alkane in bromine water. So let's start with that. Let's start with ethane. Now each of these lines represent hydrogen. I'll show it this time, but in any other molecule I draw, if I just draw a plain line, it just means hydrogen. Now along comes bromine water. So we take a small amount of alkane. No, sorry, we have a test tube full of alkane, and we had a couple of drops of bromine water. Now bromine water is like an orangey color. And what will happen is the bromine in the bromine water, it can't react with the alkane. There's no space, it's saturated. Each carbon already has 4 bonds. If it already has 4 bonds, there's no space for any additional bonds. So the bromine water goes in and it just turns to an orangey color. Now, if we do the same thing with, now let's do the same thing with ethene. So now we've got carbon, carbon double bond, and we've got our bromine. Now what happens this time is the double bond breaks. Now that double bond's broken, we've got an additional bonds that can form here and here. So the bromine forms attaches here, and the other bromine attaches here. And you'll learn about this mechanism in more detail when you do A-level chemistry. So now if you have a beaker full of an alkene and you add your orangey red bromine water, because the bromine has been taken out of the water and attached to the alkene, so it's become a bromoalkene, it becomes colorless. Okay, combustion. What happens during the combustion of alkanes? So we have methane and oxygen makes carbon dioxide plus water. So energy is released during complete combustion. The carbon and hydrogen in the fuel is oxidized to make carbon dioxide and water. So that we already know. And we've already covered this too. Methane and oxygen makes carbon dioxide and water. Now, this one is incorrect because that should be C2H6. Now, C2H6 plus oxygen gives us, because we've got two carbons, it's going to give us 2CO2. And because we've got 6 hydrogens, it's going to give us 3H2O. So altogether, that's 2 times 2, that's 4 oxygens, and 3 times 1, 7 oxygens. So that's going to be 3.5 oxygens. We can just double everything, so we can have 2 of these, we can have 7 of these, 4 of these, and 6 of these waters. Now, if there's a lack of oxygen, then incomplete combustion occurs. So if there's a lack of oxygen, incomplete combustion occurs. Methane reacts with oxygen to make carbon monoxide and water. It can also react with oxygen to make just carbon and water. Now, alkenes react with oxygen in combustion reactions in the same way as other hydrocarbons. So alkene will react with oxygen to make carbon dioxide and water, but they tend to burn with a smoky flame because alkenes are more likely to have incomplete combustion. So they can end up making carbon monoxide and just carbon, which is soot. And as we already know, carbon monoxide attaches irreversibly to the red blood cells, and then the body has to destroy the red blood cell. And the carbon can cause respiratory issues and global dimming. Okay, so what is a polymer? A polymer is a reaction in which monomers with two functional groups react and join together, usually using a small molecule such as water in the process. So this is more of an addition. This is an example of addition polymerization, or so this is an example of condensation polymerization. So when you have condensation polymerization, when condensation polymerization occurs, usually a small molecule is lost. So when we have addition polymerization, what happens here is we've got carbon double bond. Now, if the double bond breaks, then this carbon can attach to another ethene. So this was ethene initially. So let's use the example of, let's say we had 3 of these and not n. And that means we'd have 3 of these. So what would happen in this scenario is this. We would have we would have our carbon-carbon double bond, our ethene. We would have our second ethene, and we would have our third ethene. Now, they're all our monomers, and under the right conditions, polymerization happens. And what polymerization happens means, let me change the color, is that the double bond breaks. And because the double bond breaks, each one has an additional bond. So now these two ethenes can attach to each other. These two ethenes can attach to each other. Yeah. So now we made 1, 2, 3, 4, 5, 6 carbons, so hexane. Or our monomer, we've attached 3 of those monomers together. And that's what this means. So that's addition polymerization. That's addition polymerization. We know it's not condensation polymerization because nothing has been lost. We've just attached things to each other. So in addition polymerization, what happens is there are alkenes present, known as monomers, with carbon double bonds. These carbon double bonds open to form single bonds. This means that alkene monomers form long chains, and it makes long chains of alkanes. Now, this is just how you name polymers. So if you've got ethene, if you attach lots and lots of ethenes together, you get polyethene or polyethene. If you attach lots of propene together, you get polypropene. Chloroethene, you get polychloroethene or PVC, like a double glazed windows. Tetrafluoroethene, you get polytetrafluoroethene, PTFE. Okay, so this is just an example question. We'll of course do lots more practice when we do the pre-exam workshop. So we've got polyethene. It's produced from ethene. Figure 1 shows part of the displayed structural formula equation for the reaction. So it shows this side. Now on the right hand side, it didn't show the single bonds. So all you have to do is complete figure 1 by adding in these single bonds, just to show that you understand that that double bond breaks and just becomes a single bond. Now, figure 3 shows an incomplete displayed structural formula of the monomer styrene. Now, that's the polymer. So what would the monomer look like? So the monomer would have a carbon double bond, and the remaining part of this would just be single bonds. Because what's happened from here to here, that double bond's broken and just becomes single bond, which means these carbons can have one extra. Now the other thing you've got to do is put an N here. So let's have a look at this one. Complete the structure of polypropene in this equation. So propene looks like this. So polypropene, we've got N here, so we have to put an N there to show how many we're attaching to each other. The double bond breaks, becomes a single bond, and the rest stays the same. Okay, so uses of polymers. Now, what we're going to do is, actually, so I'll carry in a second. So polymers, we've got polyethylene. We can use it for carrier bags, food wrap, disposable bottles. The benefit of polymers, this polyethylene, is that it's cheap, flexible, and can be made into thin films. That's why we can use it for carrier bags. Polypropene. So all of these initially they come from crude oil. So when we crack things, we end up with alkenes. Then the alkenes can be used to make polymers. So polypropene can be used for carpets, ropes, bowls, buckets. They're strong, they're shatter resistant, and they're flexible. PVC, we can use for the insulation of electrical wire, guttering, and we can use it for double glazed windows. Now the electrical insulators, they can be flexible or hard and tough. PTFE, polytetrafluoroethene, is used for non-stick coatings for pans. if you see PTFE on a box, it's best avoided. It is slippery and unreactive, but there's some research now that shows that it does still go into the food. It's unreactive, but it comes off the pan, and it can when if it comes off the pan over time, it's going into the food. So 9.2.2 condensation polymers. What is condensation polymerization? A reaction in which monomers with two functional groups react and join together. So usually losing small molecules such as water in the process. So it just means when two different monomers with different functional groups react with each other, it causes the loss of a small molecule such as water. So, for example, what is a diol? So, a diol is a substance that has two alcohol functional groups. So, you see here, this is ethane diol, because here you've got two carbons with single bonds, so that's ethane. And then you've got two oxygens, so it's diol. Two hydroxide groups, sorry, OH groups, alcohol groups. So, when something's an alcohol, we would call it, for example, if we had carbon, carbon, we'd call that ethanol because ethane with an alcohol group. But here we've got ethane with two alcohol groups, so it's ethanediol. So the functional group here is OH. A dicarboxylic acid just means it has two carboxylic groups, as you can see here. Because carboxylic acid looks like this, COOH. So what happens during condensation? Polymerization. So if you have a diol group and you have a hexane dioic group, so you've got one that's got two, you've got one that has a functional group of an alcohol and one with a functional group of a ethanol. They can combine to make an ester. So what will happen is as you can see here, you've got with the carboxylic acid, it looks like this, and that's attached. So I'm just drawing this part here, and that's attached to everything else. And if we take this part here, sorry, this part here, then we've got now this H2O in the middle can be released. So it's a condensation reaction, so it loses that water. And by losing that water, it can then instead connect there like that. So now what we've got is this in the middle with this on one side or over here and all of this on the other side. So it's joined the ethanoic acid to the alcohol. So it's made an ester. Now the ester's functional group is, as we can see here, carbon with two oxygens. So the functional group is found in esters and polyesters. Polyester just means lots and lots of esters joined to each other. Because over here you've got COOH, so that means in theory you can attach that to another OH and do the same thing. Remove the H2O and it joins to another group. On this side here we had another OH, so that could react with another COOH to lose another water. All polyester it just means lots and lots of esters joined to each other. So in addition polymerization, you have a carbon-carbon double bond. Its monomer is an alkene or something, an alkene with lots of extra attachments. There's no small molecule that's made. That's as in it doesn't lose any small molecule. An example is polythene. Now with condensation, you could have condensation reactions in lots of different things, but for example, between an OH group, which is an alcohol group, and a COOH group, which is a carboxylic group. So monomers, you could have a carboxylic acid and you could have a diol, an alcohol. And it loses some things like water. If you join lots of them together, it makes a poly, it makes, and if you join two of them together, just one alcohol to one carboxylic acid, it makes an ester. If you join lots of them together, it makes a polyester. Okay, problems of polymers. So what are the problems associated with polymers? Um, so problems with polymers include the availability of starting materials. Um, so this is crude oil and it's a finite resource. Next problem is non-biodegradable. That this means that it can accumulate in landfill. So things like plastic carrier bags, etc. Plastic is a polymer of ethene, and these plastics are just persisting in the environment. They take over 1,000 years to decompose. And then you've got gases produced during combustion. So if you were to burn that plastic, it would release carbon dioxide and in many cases toxic chemicals as well. Plastics need to be sorted before recycling. So there are some plastics, if you put them together, you can use them for something new, but different plastics have got different chemicals added to it. Now that can be difficult and it can be expensive to do as well. And again, it does not, however, conserve finite crude oil. Because at this point, the ethene or whatever crude oil was used to make the plastic has been used. So it doesn't mean that we don't have to use the crude oil as much. We still have to use just as much crude oil. So advantages and disadvantages of recycling. Recycling saves raw materials such as crude oil, which is a finite resource. Disadvantages, there would be some issues with transportation. Recycling uses large amounts of energy. Litter needs to be sorted because people throw rubbish alongside the recycling. And recycling collection points may cause litter problems, eyesores. Okay, amino acids. So amino acids have, so if we say this is the amino acid, on one side of the amino acid, you've got a carboxylic group. And on the other side, you've got NH3, which is an amine group. So amino acids react by condensation polymerization to make polypeptides. So what happens is, let's say you've got one amino acid that's got its carboxylic group, and you've got another amino acid. Now over here, it's going to have its NH3. So here we're going to have NH3. So what will happen here is water will be made. That water will be lost through the condensation. And so now what you've got is this carbon, the double, sorry, just makes a bit more space for that. So this will evaporate, and the carbon and that nitrogen will attach to each other. And that way lots and lots of amino acids can be joined. This is called a peptide bond. And if you make enough of these peptide bonds, you make a protein. So different amino acids can be combined in the same chain to make proteins. Proteins are synthesized in the ribosome. So we know this from topic 3.8, from paper 1 biology, according to a template. So a carrier molecule brings specific amino acids. So again, we know triplet coding, three bases, then the carrier molecule brings an amino acid based on the triplet coding to add to a growing protein chain in the correct order. So it then adds another amino acid to make a polypeptide. So when a protein chain is complete, it folds up to form a unique shape. So what happens is, for example, this amino acid might be able to bond to this amino acid with a weak intermolecular bond. So lots of different weak intermolecular bonds and bonds are formed between the different amino acids, and that gives a three-dimensional shape. And that unique shape enables the proteins to do their job as enzymes, hormones, or forming structures in the body, such as collagen. Now, DNA is a large molecule which is essential for life. DNA encodes genetic information for the development and functioning of living organisms and viruses. So DNA is a large molecule, but this we already know. So most DNA are made up of two polymer chains in a double helix. The polymer chains are made from four different monomers known as nucleotides. So we've got this one here, G, C, T, and A. And these are the four different nucleotides. And you can see the nucleotide is made up of a base, a ribose sugar, and a phosphate group. As you can see here, so we've got a phosphate group, a sugar group, and the base. And DNA contains four different bases, A, C, G, and T. A sequence of three base codes, a sequence of three bases codes for an amino acid. The order of bases controls the order in which amino acids are assembled to produce a particular protein. C is always has a complementary link with G, and T always has a complementary link with A. Okay, so let's have a look at some other examples of naturally occurring polymers. So a lot of these we already know. So a glucose molecule is the monomer. Attach lots of them together and you make starch, and you can also make cellulose. We already know this one. If you attach lots of amino acids, to each other, you make a polypeptide or a protein. And each one has its own use. So proteins we need for growth and repair to make enzymes. Starch is a way of storing energy. Cellulose strengthens the cell wall. DNA provides genetic information of the organism. So all these are polymers, but naturally occurring polymers. Okay, alcohol. Now, alcohol, if we say methanol, the ol part means that OH has been added to it. So if it says methanol, we need to say, this is what we need to do. Meth means one, meth means one, methanol means one carbon. If it's anol, the ol word is there, then we add an OH. Now, carbon has four bonds, so we just complete the four bonds. Right, so now let's try ethanol. Eth, what does eth mean? Two carbons. So we draw our two carbons. Anol, the ol means it's got OH group there. And then we just need to now complete the hydrogens. So this carbon's got one bond already. 2, 3, 4. This carbon here already has two bonds, so we're giving it two more bonds, so it also has four. So what you probably noticed is, if you look at the number of carbons, if you double the number of carbons plus one and then you add OH at the end. So the hydrogens are always twice the amount plus one, and then you add OH also. Now this H, as in we can't write, when we write C3OH, we can't call it CH4O. It's, you got to show the OH because that's the functional group. That's the part that reacts. Okay, core practical. How can we investigate the temperature rise produced? How can we investigate the temperature rise produced by the combustion of different alcohols? So you place 100 centimeter cubed of water into a beaker, measure the mass of the ethanol in the burner, place the burner under the beaker of water and light the wick. Heat the water until the temperature has risen by 30 degrees, extinguish the flame, determine the new mass of the burner. So now we know how much of that particular alcohol was used to heat up by 30 degrees. So you do the same for methanol, ethanol, propanol, butanol, and see which one provides the most energy. So how much of it gets used up, increasing the temperature by 30 degrees. So when alcohols react with oxygen, if you get similar to a complete combustion of but you get exactly the same as complete combustion of ethane and ethene, because methanol is made up of carbon, hydrogen, oxygen, and you're reacting with oxygen. So the only two things you can make are carbon dioxide and water. Now, what I'd advise is just going through a few of these and making sure that you can balance them. So if we're talking about propanol plus oxygen, then we mean C3, double it plus one, so 7, OH plus oxygen gives us, now we've got 3 carbons here. So that's going to be 3 CO2. And we've got 7 plus 1, 8 oxygens, 8 hydrogens. So that's going to be 4 H2O. So what that means is, now that first one's not balanced in the first place because that's 1.5 oxygens that are needed. Now here, if you look at it, we need 6 oxygens plus 4, so we need 10 oxygens. Now we already have 1 here, so that means we need 9 more. So that would be 4.5 oxygens. So you can just double the whole thing. So we can double it by just changing it to 2 of these, 9 of these, 6, and 8. But half is fine. So that's what it's showing here. 2, 9, 6, 8. You don't have to double it. You can put it as a half if you want to. Okay, carboxylic acid. So we've already established that a carboxylic acid is an oxygen group and OH group attached to a carbon. That's the functional group of carboxylic acid. So again, make sure you're familiar with the formulas and the diagrams. Check out some past paper practice. Now, what happens when carboxylic acids react? It's the same as what we've learned before. When an acid reacts with a carbonate, it makes, now this is a carboxylic acid, but a carboxylic acid, an amino acid, hydrochloric acid, ethanoic acid, but this is ethanoic acid, nitric acid, sulfuric acid, doesn't make a difference. If it reacts with a carbonate, it will always make salt plus water plus carbon dioxide. Now, if a carboxylic acid reacts with an alcohol, this links back to condensation polymerization, which means when they react together, it makes an ester and it also makes water. Because as I was saying to you guys before, the only thing that I made a mistake on before is that it's the full OH group there and the H. It comes from the alcohol. I was taking the OH from the alcohol. It's only the H that comes from the alcohol. So I was doing both that with the H. That's incorrect. It's the OH from the carboxylic acid. So there's your alcohol and there's your carboxylic acid. Okay, so what are homologous series? These are molecules with the same functional group. This means the molecules in the same homologous series react in a similar way. That's because they have the same functional group, they react the same way as well. The functional group is the part that reacts within the molecule. So it doesn't matter if you've got carboxylic acid with one carbon, with two carbons, with three carbons, with four carbons. If it's got a carboxylic acid attached at the end, then the reaction is still going to be, they're all going to react in a similar way. Okay, production of ethanol. So solutions of ethanol are made when sugar solutions are fermented using yeast. So you've got your yeast, which is a living thing. It uses the sugar to respire. Now, if you do anaerobic respiration, as in you get rid of the oxygen, then it makes two things, carbon dioxide and ethanol, which is alcohol. So as long as not you, but as long as the person keeps the yeast, the sugar, and at between 25 to 35 degrees, that which is optimum for a yeast, then ethanol will be made at the end. So alkene plus water makes alcohol. So what happens when alkenes react with water? So you can make, this is this other way of making ethanol. So this is one way. You can do fermentation, which takes place anaerobically without oxygen. So yeast feeds off the sugar, it anaerobically respires, and it makes ethanol. The second way is using an alkene. So for example, do ethene plus water. There's your carbon-carbon double bond. There's ethene, C2H4. Now let's add some water to it. Now water is H and an OH. So what will happen is it will cause a break in the bond here, and this H here will attach there, and the OH will attach here. So what have we just made? C2H5OH. We made ethanol. Now, what are the uses of alcohols? So ethanol is an alcoholic drink, like for example, wine and beer, but it can be used for fuels. It can be used as solvent. So if something doesn't dissolve in water, it can be instead dissolved in alcohol. So when you're doing chromatography, you can use ethanol instead of water if you've got a solvent that won't move up the chromatography paper. So solvents in markers, pens, medicines, perfumes, and deodorants. So how is concentrated ethanol obtained from a fermentation mixture? Now, this is just really simply, this is distillation. Now, over here, if you've got a mixture of, so when you do a fermentation reaction, after around 15%, after 15% of ethanol is produced, so the yeast starts to make ethanol. When it gets to about 15% ethanol, it poisons itself. So all the yeast dies off. So what you've got is water, you've got the fruit juice kind of sugars in there, and the other thing you have in there is 15% alcohol. So now if you take that 50% alcohol plus the water and someone wants to make that pure ethanol because for whatever use, then all you're doing is ethanol has a lower boiling point than water. So if you take this to about 70 degrees, the water evaporates, and so the ethanol evaporates, It goes through the condenser when it's cooled down and it condenses, turns back into a liquid, and it can be collected here. Water's left behind there. Now you will get some evaporation of water, so you will have some water with the ethanol, but it'll be much more pure ethanol compared to what it was initially. Okay, nanoscience, nanoparticles. So nanoscience refers to particles between 1 to 100 nanometers. So nanometers means times 10 to the power of 9, minus 9, sorry. Now, these structures contain a few hundred atoms, and so they're very small. Nanoparticles are small, smaller than fine particles. Sea spray is an example of nanoparticles. Now, when we say fine particles, that means they have a diameter of between 100 to 2,500 nanometers. So you've got nanoparticles which are between 1 and 100. Then you've got fine particles which are between 100 and 2,500 nanometers. So 1 nanometer to 100 nanometers is nanoparticles. So 100 to 2,500 would be fine particles. And an example of a fine particle is the smoke that comes from a candle. Then 1 times 10 to the minus 7 to 2.5 times 10 to the minus 6. This is an example of, so this is 10 times 10, sorry, 10 micrometers to 2.5 micrometers. No, sorry, 0.1 micrometers to 2.5 micrometers. That's an example of a coarse particle. So a coarse particle would, for example, be dust. Okay, so how is surface area calculated? Because what nanoparticles provide is for the volume, they provide a large surface area. They've got a massive surface area to volume ratio. So you want to work out the surface area of that cube, you work out the area of that one surface, that one square, which is length times width. And because there's 6 faces on a cube, you just multiply that by 6. If you want to work out the volume, you do the length times the width times the depth times the height, whatever you want to call it. You multiply them and you've got the volume. Now, if you've got a cube that's 10 centimeters, one side is 10 centimeters, your surface area, so one side is going to be 10 times 10, then you multiply that by 6 because there's 6 sides. So it'll be a 6 centimeter squared um, surface area. But the volume will be 10 times 10 times 10, which is 1,000. So surface area to volume ratio is 600 to 1,000, 0.6. But if you have something smaller, then each side is 1 times 1. Multiply that by 6 because you've got 6 sides. You've got 6 centimeter squared surface area. But the volume is just 1 times 1 times 1. So we have a ratio of 6 to 1. That's a massive surface area to volume ratio. So why do nanoparticles have different properties to the same material in bulk? And a big part of that is because they've got larger surface area to volume ratios compared to the bulk material. And because of that, nanoparticles have different physical and chemical properties, including how quickly they react, their melting points, the optical properties, everything is different. So that's why we can use nanoparticles as catalysts, cosmetics, we can use it in sun cream, medicine, electronics, deodorants. Because a nanoparticle, for example, if you've got a nanotube, it's very small, it can get through membranes, and it means you can put a medicine inside it, a medicine that might have a charge and might struggle to get through membranes. You can put it inside the nanotube, and because it's within that tube, it acts like a carrier for that drug because it's hollow. So what are the advantages and disadvantages of nanoparticles? So nanoparticles, so excuse me 1 second. Nanoparticles, they are advantageous because they catalyze reactions more efficiently because the surface area is so big compared to the volume. You don't need to use as much of it to increase the speed of the reaction. It catalyzes different reactions and that make different products, so it can be used in lots of different products. It's cheaper because less is needed. Now, if we breathe it in, it could cause harm. It could catalyze reactions in the body that are harmful, and toxic substances could bind to the nanoparticles, causing harm. Because that means if the nanoparticle becomes a carrier for a toxic substance, that toxic substance can go through our membranes into our body. Okay, glass, ceramics, and polymers. Most of the glass that we use is soda lime glass, and that's made by heating a mixture of sand, mainly sand, sodium carbonate, and limestone. Now, borosilicate glass, so this is the point that's being made here, is that just by adding something to it, by adding boron trioxide, it means that that glass can melts at a high temperature. So it can be used to heat things up. Now, clay ceramics, including pottery and bricks, are made by shaping wet clay and heating them in a furnace. Now, we've got two examples here of, of different types of polymers. So properties of polymers depend on what monomers they're made from and the conditions in which they are actually made. So when you make high density polythene, it's made at low pressure. And what it does is it makes the bonds more uniform and it has stronger bonds attaching each of these layers. So you make what's made from it is quite strong plastic materials, such as pipes for water to flow through. Now, this low density polythene is made using a high pressure and a slightly lower temperature. So that makes a more flexible plastic, the kind of plastic that we use in our carrier bags. Thermo-softening polymers, they melt when they're heated. That's because there's no strong bonds between the chains. Whereas thermosetting polymers do not melt when they're heated. That's because you've got these strong bonds between the chains that stop them from sliding over each other. So this is a thermo setting polymer. Okay, so alloys. Alloys are harder than pure metals. Now, in a pure metal, just like in a solid, the atoms are in regular layers, which means they can slide over each other. But in an alloy, the atoms in the alloy are of different sizes, so it disrupts the layers. So the layers in the alloy are distorted or disrupted. Because the layers are distorted, they cannot slide over each other as easily. So an alloy is a mixture of two or more metals, or a metal and a non-metal. The example of an alloy metal would be iron and carbon, which is steel. Steel is made of iron and carbon. Okay, composites and metals. So let's look at some examples of alloys. Bronze is made of copper and tin. Brass is made of copper and zinc. So usually when you add two different metals, then the metal that alloy that's made from it takes properties and qualities from both. So here brass is harder than copper, but it's still malleable. So you've got example of steels. Now steel is usually carbon and iron. Well, when there's too much carbon, it makes it very strong, but it's brittle. When there's low amounts of carbon, it makes it softer and it's easy to shape. Stainless steel is made from iron, chromium, and nickel, and that's really useful because it's hard and it does not rust. Aluminium alloys are really useful as aircraft in drink cans and cars because they have low density. Now, when we say most composites, when we say composite, we mean a material made up of two or more materials with different properties that are combined to make a material with improved properties. So the matrix or the binder, that's the main material. It acts a bit like a glue. It surrounds and binds together fibers. Now, fibers we call reinforcement. So, for example, when you make cement, I think it's on the next slide. When you make concrete, you get cement. Cement is this kind of thick, gloopy stuff that acts a bit like the glue. And to convert cement into concrete, you add small stones, aggregates, small little bits to it. It's usually small or large stones. And then overall, the concrete becomes a lot stronger. Now, if you add this metal to it, it also adds further strength and it also adds flexibility to the concrete as well. In fiberglass, it's made of like a special resin, and that's the resin makes up the matrix or the binder, and then it's got little tiny bits of a type of glass that comes together then to make fiberglass, which is very, very strong.